Okay, awesome. So welcome. Thank you so much for joining us today. It's the last day of this awesome Indaba, and of course we are so excited to have you here with us for our very first quantum computing and quantum machine learning for Africa workshop here at Indaba. So at the end of the day, I think this workshop is meant to be all about you and also about building the community around quantum. So it's not just about us as presenters speaking to you, and that's why I've been urging all of you to please come closer together. We want you to really be focused on building this quantum community in Africa. Okay. So just a couple of things. Obviously, the program has shifted quite a bit, so please do bear with us as we try and catch up on time. But for the basics, I'll just be doing a few introductions, and then we'll hand over to Ryan over here. So if you haven't yet met him, please do come and chat to him. He is from AIMS in South Africa, and he'll be doing our keynote on foundations and where we see Africa going with regards to quantum. And then I'll hand over to two of my colleagues. They've really been so pivotal with putting this workshop together. Niase from IBM Research, and we've got Yusra as well. They will both be taking you through foundations and getting a bit more into the nitty-gritty of the algorithms.
A classical computer is basically any object that can satisfy 4 criterion. The first criterion is that it should be a collection of bits. And so basically, like, this is what a computer is fundamentally, a collection of bits. And these are just any physical object that can be in one of 2 states, either 0 or 1. And you can think about this like geometrically or visually as arrows that are just up or down. And indeed, if you wanted to, you could build a computer out of light switches. You could really build a computer out of anything that can be in one of 2 states. Okay, and so your initial state of the system is some bit string. And then the next thing you have to do is you have to be able to turn the computer on and know what's going to happen when you turn it on. So basically, you have to have the ability to prepare some fixed initial state. If every time you turned your computer on, it was in some different state, it would be impossible to do computations. So you have to have the ability to initialize the computer in a state that you know. And typically, it's convenient to just assume that you always prepare the computer in the state where every bit is all 0. OK, now you want to do a computation. And in this abstract language, what is a computation? Well, a computation is some transformation of bits. And so what you have to do is you have to have the ability to implement an arbitrary Boolean function, some function that takes some bit string to some other bit string. And this function is really the computation. Every single time you do anything on your computer, some Boolean function is being implemented that maps the state of the bits at one time to the state of the bits at another time. And finally, you need to be able to read out the solution. So like once you've done this transformation, if you've done it correctly, then the state of the bits after the transformation should encode the solution to some problem. And you have to be able to look at the computer and see what the solution is. OK, so this is kind of my very abstract, zoomed out perspective of what a computer is. And I think this perspective is very helpful in introducing what a quantum computer is. But one question you might immediately have is, OK, the ability to implement some arbitrary Boolean function seems very difficult. This scales doubly exponentially, the number of such functions. But it turns out that actually it's kind of easy to do this. You just have to be able to implement some small set of universal gates. Like and or not, for example, is totally sufficient. And if you can do those, you can chain them together to do an arbitrary computation. And so if you want to build a computer, all you really have to figure out is in some specific physical system, how do I realize an and or a not gate? OK, so like I said, like this is an abstract perspective. And if you want to build a physical computer, you just need some physical system which can realize these 4 properties. And the one we've kind of converged to is transistors. And away we go, and we build classical computers. OK, so what is a quantum computer? So a quantum computer is essentially an object that also satisfies 4 very similar properties, but with some small differences. OK, the first thing is that instead of being a collection of bits, a quantum computer is a collection of what we call qubits, or quantum bits. And remember, a classical bit was just like something that's either 0 or 1. And a quantum bit is a unit vector in C2. OK, so you imagine like C2 is a 2-dimensional vector space. It has a basis. It has 2 basis vectors. We label one of them 0 and one of them 1. And a qubit is just any physical system whose state is described by a unit vector in this 2-dimensional vector space. OK, and now there's a nice isomorphism between C2 and R3, this polar decomposition. And so you can represent a qubit as an arrow on a sphere in 3-dimensional real space. And so now this is nice. You kind of see how qubits generalize bits, because remember, bits are just arrows that point either up or down at the North Pole or the South Pole. And a qubit is just some physical system whose state is described by a vector that points at the surface of a ball in R3. OK, great. That's a qubit. Again, like, this is my mathematical perspective on it. Later, you will hear a lot about the physics of this. And like, what to me is interesting about quantum computing is you can approach it like a mathematician or a computer scientist like I do, completely ignoring all the underlying physics. Or you can come at it from a physics perspective, which is really interesting, and you'll hear more about in the talks later. OK, so now just like a regular classical computer, when I turn the computer on, I should know what's going to happen. And so again, I should be able to prepare it in some fixed initial state. And here we just say, let's imagine we can prepare all the qubits in this like 0 basis state. Let me fiddle with this. OK. Now, in a regular computer, we know that the transformation should take us from a bit string to a bit string. Now, in a quantum computer, we need a transformation that takes us from a unit vector or a collection of unit vectors to another collection of unit vectors. And well, from linear algebra, you might already know that the set of transformations that preserves norms and inner products is unitary transformations. And so the analog of the arbitrary Boolean function in the classical case is an arbitrary unitary transformation in the quantum case. And this guarantees that if you had a valid state of qubits going in, you will have a valid state of qubits going out. And now finally, you need the ability to read out the results of the computation. And how do you do this? Well, you make measurements of the systems which realize the qubits. But the interesting thing about quantum computing is that when you measure a physical system, what happens is not deterministic. If you measure a quantum system, like if you prepare and measure a quantum system over and over again, each time you will get a different outcome. But like all you know is the probability distribution of that outcome. So if you measure this quantum system, maybe the first time you do it, you'll get that bit string. The second time you do it, you'll get another bit string. And ultimately, what you're doing is you're sampling bit strings from some distribution, which is determined by the unitary operation. And in classical computing, the goal is to like derive a Boolean function such that the bit string at the end is the solution to the problem you want. And in quantum computing, the goal is to design a unitary operation such that this probability distribution over measurement outcomes is peaked on the solution to the problem that you want to solve. So here the computation is defined by the unitary, and now the solution is defined by the probability distribution over measurement outcomes. And if you've done your job well, then like with high probability, you should get a bit string that encodes the solution to the problem you're interested in, the correct protein configuration, or the optimal route for the DHL driver to deliver packages, for example. OK, so this is my abstract presentation of what a quantum computer is. And like I said, later you'll hear a more physical and historical perspective. But at least if you come from a sort of mathematics or computer science background, I think this is a helpful picture. OK, and again, here, like it turns out to be easy to implement arbitrary unitary operations. You just have to be able to implement some small subset of universal gates. And indeed, that's what people who build quantum computers have focused on doing. OK, so I've told you now what a quantum computer is. And this whole workshop is about quantum machine learning. But really, like so far, you have no evidence that quantum computers are interesting. But let me now try convince you. So a game that computer scientists like to play is to categorize problems into the difficulty of solving them. This is a branch of mathematics called complexity theory. And roughly, we have the following categorization. All problems that can be solved efficiently, so that you have like a reasonable chance of solving with your computer, we call these problems P. They can be solved in polynomial time, where polynomial is just jargon for a reasonable amount of time. And then there's a bigger class of problems called NP, and the name is not so important, but these are the problems where it's very easy to check that a solution is correct if you're given one, but at the moment we don't know of any algorithm to solve it efficiently. And really, NP is the class of problems that we would love to have good algorithms for. NP includes problems like finding the optimal route for a delivery driver, for example. The traveling salesman problem is an example of an NP problem. OK, and in fact, it's an example of an NP-complete problem, which is kind of the hardest problems in NP. It turns out if you can develop a good algorithm for just a single NP-complete problem, you immediately get an algorithm for all NP problems. OK, so now, like, in order for quantum computers to be interesting, we can define then the class of problems that can be efficiently solved with quantum computers. And we can call that set BQP for, like, the Q is for quantum and the P is for polynomial. And now, in order for quantum computers to be interesting, it should be the case that the set BQP is bigger than P. If the set BQP, the set of problems that can be solved by quantum computers, was smaller than the set of problems that could be solved by classical computers, there would be no reason to build a quantum computer at all. And so this is really the big question. In the 90s, when people kind of invented this idea of a quantum computer, they drew this diagram, and the first question was really like, how big is that set BQP? And so it turns out that it's still a huge mystery, like where exactly that set BQP lies. But the good news is that we know that there's at least one problem, the problem of factoring integers, which we don't believe is in P, but thanks to someone called Peter Shaw, he came up with a quantum algorithm for it in 1994. And so now we know that there at least exists one problem, which we can solve efficiently with a quantum computer, but no efficient algorithm is known for classical computers. So this is evidence that like there's something interesting going on here. And of course, the key question is, are there more? And kind of like quantum algorithms research can be summarized as, are there problems which lie outside of P, but inside of BQP? And really, this is kind of what everybody in the field is working on. But I should point out that also, even if it turns out that there's only factoring that is outside of P and inside BQP, we still learn a lot of very fundamental physical things by thinking about quantum computing. Quantum computing really forces us to think about the physical nature of information and what is possible in terms of information processing in our universe and in physical systems. And also, like, trying to build quantum computers has led to like many incredible insights about the nature of matter itself, because ultimately when you try to build a quantum computer, you're trying to manipulate nature at the most fundamental level. Okay, so this sounds great. Quantum computers sounds amazing. They can factorize numbers. Like, where are they? And so in around 1985, when Feynman and some other people came up with the idea of a quantum computer, quantum computers were really just these mathematical objects, and quantum algorithms existed as drawings on pieces of paper. Now, we really have quantum computers, and they have on the order of more or less 100 qubits. And investment in quantum computing has taken off incredibly. Like, all major nations and governments have invested incredible amounts of money. All the big tech companies have quantum computing programs and are hiring like crazy and trying to build as good teams as they possibly can. And what's even more interesting is that you can actually use these quantum computers. So IBM and other companies allow you access to their quantum computers via the cloud. And so if you want to like play around and explore and run algorithms on quantum computers, you can do this. And I should stress how incredible this actually is. So in the last 5 years, there's been 2 Nobel Prizes awarded for quantum information. And these Nobel Prizes were awarded for manipulating quantum mechanical systems at like the atomic level. And every single time you run a quantum computation on one of these IBM quantum computers, you are doing exactly that. You are doing exactly the thing that all these Nobel Prizes were awarded for. So this is really sort of like an opportunity for citizen science that is somehow unprecedented in history, I would say. Okay, so now like I've told you that you can factorize numbers efficiently using a quantum computer. And maybe some of you have a background in cryptography, or maybe some of you kind of have heard that, well, all of our like digital information is kept safe by the assumption that factorizing numbers is hard. There's this crypto system called RSA, and it's used to encrypt our data on the internet. And it turns out that if we had a good algorithm for factorizing numbers, we could break this crypto system. And now we know that quantum computers can do this, and we have quantum computers. So like, are our credit card details safe, basically? And unfortunately, it turns out that the quantum computers we have at the moment are not as good as we want them to be. And there's this thing called noise, which is a major obstacle. So what is noise? So imagine you want to implement a quantum circuit. So this is what a quantum algorithm is. It's some sequence of quantum gates. What happens in practice when you try to do this is that you try to do the gates, and some like unintended errors will always occur. So quantum gates at the end of the day are happening like physically. A laser is being shot at some ion like that has an electron kicked out of an energy level, or a voltage pulse is being applied to some superconducting circuit. And so many different things can make this go wrong. Slight calibration errors can cause the voltage pulse to be applied for a nanosecond too long. Or a cosmic ray can come and interact with the system. These are the sorts of things that can go wrong in quantum computers, and they do. And the net result is that the thing you get out the end is basically just junk, to be honest, and completely uncorrelated with what you would want. And if we want to build quantum computers, we need to address this and think seriously about it. And people have realized this since the early 90s and invented this discipline called fault-tolerant quantum computing. And there, basically, the idea is that, okay, well, what you do is instead of having one qubit, like you have multiple qubits, you kind of make the information redundant. And then you design some system such that after you've done the gate and after the noise has occurred, you interact with that system in such a way that you can kind of get some information that then allows you to determine what operations you should do to correct the errors that have occurred. And if you design the system well, you can kind of do this indefinitely, and in the end, you end up with the correct result. And this is an extremely active field of development. So on the archive, every day, there's 10 to 20 papers on quantum error correction, and we're making drastic progress. And at some point, I believe, and I think the majority of the community believe, we will really have fault-tolerant quantum computers. But right now, we do not. And the reason is because the overheads you need to do this are massive. For every single qubit that you really want, you need maybe like 100 or 200 qubits to facilitate the error correction. So now we're in this so-called regime of noisy intermediate scale quantum computing, where basically we say like errors happen, and therefore like if we want to do something interesting, we just have to use short circuits. Basically our circuits have to be short enough that the errors don't accumulate in a way that creates junk at the end. So basically in the NISQ paradigm, what we try to do is quantum computations with limited depth. Okay, and that's now. And so there's kind of these two groups of people in the quantum computing community. Some people are trying to figure out how to build fault-tolerant quantum computers. Other people are trying to figure out what you do once you have a fault-tolerant quantum computer. And other people are saying, we have quantum computers now. What can we do with them? And in this talk, I'll kind of talk about both aspects a little bit. Okay, so firstly, like, what can I do with a fault-tolerant quantum computer? Or what should I hope to be able to do with a fault-tolerant quantum computer? So I think we can summarize the current state of affairs like this. And this is thanks to someone called Lin, who created this kind of way of visualizing things that I really love. So basically, we draw an XY axis. And on the x-axis, you can put the range of scientific or industrial applications. And on the y-axis, you can put the existing evidence that we have of a quantum advantage, that a quantum computer would be able to do any better than a regular computer, than a classical computer. And then you can imagine the sort of applications as a pyramid. And at the top is cryptanalysis, so breaking cryptographic codes. So we've known since the 90s that if you have a quantum computer, then you can factorize numbers, and this allows you to break the RSA crypto system. And this certainly has some applications, especially if you're a government and you want to learn the secrets of other governments. Like, you can use quantum computers for spying, and et cetera, et cetera. But I would argue that if you're a scientist, or if you want to start a company, this is not so interesting to you. And so there's another category of problems which I can call quantum mechanical problems. And here we also have pretty good evidence that quantum computers will get an advantage, and they have slightly more applications. So this is things like simulating chemical, biological, or physical systems whenever like quantum mechanics is involved. So for instance, many drugs, they work at a quantum mechanical level. You really have different atoms interacting with each other in certain ways, and whether or not the drug works relies on simulating the quantum mechanics of those interactions. And it turns out this is very, very hard to do with regular computers. And we have good evidence that quantum computers will be better at this because they are quantum mechanical systems themselves. You could imagine setting up the qubits to kind of model the different atoms that are involved in this chemical process that you're interested in. And then the unitary models the process that happens. Okay, and this has vast applications in sort of medicine and material design. And I think this is where most of quantum algorithms research is focused, on quantum algorithms for these quantum mechanical problems. And then at the bottom of the pyramid is fully classical problems, things like solving linear systems, differential equations, optimization, machine learning. So this is kind of everything else, and the vast majority of things that people actually use high-performance computing for. But to be honest, even though like this is the most widely applicable class of problems, it's also the class of problems that we have the least evidence of quantum advantage for. So you hear things all the time, quantum machine learning will revolutionize the world, quantum optimization will solve climate change. Honestly, we don't have any evidence for this at the moment. Like, we really don't, and this is a very active field of research, but I think it's good to kind of set the expectations. And what we know is that this is the class of problems we would love quantum algorithms for because they're so widely used and so widely applicable. But the truth is right now we don't have very good evidence that they're advantageous. And so what I'm going to do in the rest of the talk is I'm going to kind of walk you through a little bit of a narrative of like how we've developed our understanding of what may or may not be possible in this bottom row for machine learning in particular. Obviously here people are particularly interested in machine learning, and I'm going to kind of trace my personal journey of understanding of what might or might not be possible for quantum machine learning algorithms. Okay, and I'm going to talk about a very, very specific type of quantum machine learning called variational quantum machine learning. So what is variational quantum machine learning? So the idea, and this is going to sound like jargon for now, but I'm going to explain it, is to use parameterized quantum circuits to define learning models. So for me, a model is just going to be some like set of functions, for example. So you know that neural networks, all they're just some set of functions that you can easily optimize over. And now the idea is, can we use quantum circuits to define some set of functions that we can easily optimize over, or distributions, for example? Okay, so imagine as a toy example that you want some function which maps from R3 to the interval 0, 0, 1. And this means that the input to your problem is some vector that consists of x1, x2, x3. And now how can I use a quantum circuit to realize a function from R3 to 0, 1? Well, what you can do is you can take the quantum circuit, and then you can make some of the gates depend on the input to the problem. So for instance, like on a quantum computer, like one set of gates are gates that rotate the state of the qubit around an axis of this sphere, and like you will see again this in more detail later. And you can say that, oh, let me just parameterize that rotation by the input. So like the amount that I rotate in the gate is determined by the input. And then you can, so there's some input gates, and then you can have some other gates which depend on parameters that can be optimized. And when you do this, what you end up with is a unitary that depends both on the input and on some variational parameters. And like I want you to see that this is very analogous to neural networks. In neural networks, you have some layers at which the data enters, like either the first layer or like in ResNets, like at some higher layer. And then you have some other layers that depend on variational parameters. And at the end, what you get is some function which depends on the data and the parameters. And here, what comes out of this quantum circuit is a quantum state that depends on like the input data and variational parameters. And now what you do is you measure it. And like I told you, each time you measure it, you're going to get a different outcome. But if you wanted just one number, what you could do is you could take the average of all those different outcomes and define this as the value of your function. So this is a way to define a parameterized function by a quantum circuit. And when you do this, what you get is that you could imagine the set of all functions. And now once you write down a specific quantum circuit with a specific set of gates, you will be able to realize some other set of functions, and this is the learning model. And on this diagram, I could also draw, for example, all the functions that can be realized by neural networks with 10 layers and width at most 100. The point is that a learning model is a subset of functions, and just like we can use neural networks to come up with some subset, we can also use quantum computers to come up with another subset, and the question is whether or not this is an interesting subset for learning. Okay, and let me point out that you can do exactly the same thing for probability distributions. And in fact, for probability distributions, it's very natural because you have a quantum circuit, you define some gates which depend on data that can, parameters that can be optimized. And you know that when you measure the outcome of the circuit, you're going to sample from some probability distribution that's determined by the data. So quantum circuits actually provide very, very, very natural probabilistic or generative models. And again, depending on the circuit you write down, you're going to get some subset of distributions. Okay. Now, how do we use these in machine learning? Exactly the same way we use neural networks. We take the outcome of the function or the distribution, we send it to a classical computer, which makes some decision about how we should update the parameters, and then we keep going in a training loop until we converge to parameters that we think are optimal. So this is what people call the variational approach to quantum machine learning, and the idea is really to kind of make an analogy of what people do with objects like neural networks. Okay. So now you understand like what variational quantum machine learning is and what the idea is, and like what would we want? Okay, so I'm a mathematician, and like I often imagine when I'm like trying to figure out like what problems I should solve, that I have like some black box, magic box that I can push, and just like my dream theorem comes out of it. And what would my dream theorem be? Because then I can focus on trying to prove that theorem. And ideally, what I would want is I would want a rigorous guarantee for like a state-of-the-art learning framework on real-world data sets. So I would love it if I could prove like upper bounds on the amount of data or the amount of time or the generalization capacity of these sorts of models for things like neural networks or for parameterized quantum circuits on real-world data like natural language or protein shapes. I mean, really, if I had a theorem that said that for all proteins in this class, if you want to be able to predict their structure up to like 2% accuracy, then you need at most 17 examples. This would be like a dream theorem that would be very useful in the real world and allow people, like provide real guidance to people using these. But even better, of course, would be if we could prove what we call quantum classical separations. So if I could prove that, imagine I could prove that if you want to solve this problem classically, then you need at least some amount of data. But if you want to solve it quantumly, then you need at most some amount of data, which is less than the amount of data you need classically. If I could prove a theorem like that, you would immediately say, give me quantum machine learning. Like this, it proves an advantage for quantum machine learning. You could also do the same thing with accuracy. You could fix the amount of data, and you could try prove that the quantum algorithm will achieve at least some accuracy. while a classical algorithm could achieve at most some accuracy which is less than that. So kind of what I've been trying to do for the last few years, or what a lot of people have been trying to do, is prove theorems of this type. Okay, but this is super hard. Like really, this is very, very hard. And in classical machine learning, like if you prove a theorem like this for neural networks or something like this, you will get a spotlight talk at NeurIPS. This is like hard, complicated mathematics. And so like, how can we get what we want? Well, the first thing you learn when you like start doing research is that you should simplify the problem. Like always, like you want to solve some problem, you think, what is the simplest version of this problem that I can solve? And so what is the simplest version of this problem that I can solve? Well, we'd like to kind of prove theorems about data sets like ImageNet, the stock market, protein configurations. And we would like to prove separations between, like, for instance, parameterized quantum circuits trained with stochastic gradient descent and classical algorithms. But this seems super tough and out of reach. So the first thing we can do is we can say, like, let's throw out this like generic data that's in the world, and let's replace it with some fine-tuned data set. Let's rig the game in favor of the quantum algorithm. Let's try come up with a problem where the only point of this problem is to prove that quantum machine learning can do better than classical machine learning. And like, basically, even though this feels unfair, my argument is that this is kind of a necessary but sufficient condition. If you can't prove that a quantum computer is better at machine learning for a problem that you've designed for the quantum computer to be better at, then I would say that you should really not yet try prove that quantum computers can be better at real-world tasks. And the nice thing about this is also you can consider problems that have like concise mathematical descriptions that you can hope to prove theorems about. And you can also encode problems that you already know are provably difficult for classical computers. Okay, and again, you can rig the game even more and say, like, even though I would like to know something about variational quantum machine learning, let me maybe first just consider like some fine-tuned quantum algorithm again. So let me restate the caveats that this is not generally applicable. Like, we're going to tailor it to exploit the specific data set structure. And maybe this fine-tuned learner would even require a fault-tolerant quantum computer. And so if we can prove a quantum classical separation in this setting, it really would provide no evidence at all that in the real world, quantum machine learning could be better than classical machine learning. But it's really a necessary condition and like a first step to hopefully proving advantages in more generic settings. And if you do this, you kind of develop your toolbox a little bit, you learn how to prove things, you get a little bit more intuition about what quantum computers are good at. Okay, and so it turns out you can play this game and you can do it for generative modeling, you can do it for density modeling, you can do it for supervised learning, you can do it for reinforcement learning. For every branch of machine learning you can think about, people have managed to construct like finely tuned problems that you can prove that no classical algorithm could solve efficiently, but there exist quantum algorithms that can solve it efficiently. But like I said, this is a very rigged game. And to do this, you use cryptography, and I'm gonna skip this, how that works. Okay, but now we want to like relax some of the fine tuning. We kind of did the first homework exercise, and now we want to do the second homework exercise, the one like that's marked with some star. And so basically, like you drop the fine-tuned data set. So we say like, let's drop the fine-tuned learners and consider the actual machine learning algorithm we want to consider, like a parameterized quantum circuit updated with some form of stochastic gradient descent. And now we want to have a slightly less fine-tuned data set. And so you can ask yourself, what is the problem that I expect parameterized quantum circuits to be the best at solving? And if you think about this for a little bit, maybe you would end up on saying that, well, I think that the functions that parameterized quantum circuits are going to be best at learning are those that can be realized by parameterized quantum circuits themselves. Or in the distribution case, we know that there's some set of distributions that can be realized by measuring quantum circuits. Maybe I should try study the problem of learning those distributions themselves, because I really know that those can be represented by quantum circuits, and so I expect them to be very good at it. And so this is not yet like things like natural images, but it's hopefully generic enough, or at least it's a step in the right direction. And so here, if you manage to prove a quantum classical separation in this setting, you would give some evidence in favor of quantum machine learning models, in the sense that you would say like, okay, this is not so fine-tuned. It's like more towards the real world. But importantly, if you can prove that no separation is possible in this setting, then you've given pretty strong evidence against quantum machine learning with variational quantum circuits. And so this is nice because no matter which way you prove this theorem, you win. Either you prove that, okay, there's something in quantum machine learning, or you rule it out and you say that, okay, like this is not a promising approach because the one problem we expect them to be best at, there can be no advantages. And so if you play this game, you can prove actually that this problem of learning the outputs of quantum circuits is actually hard for variational QML. It's hard for classical machine learning, and it's also hard for quantum machine learning. And in fact, it's not actually hard, it's extremely hard. And this has a technical meaning, which I can explain if anyone is interested. And so basically, this is kind of bad news, or it's a roadblock, and it kind of points to a limitation of variational quantum machine learning. That says that we're unlikely to get a quantum advantage from these sort of parameterized quantum circuit machine learning models. Okay, so what is the takeaway from this? Like, what message should you take from this? Firstly, we can get provable quantum advantages in machine learning for very contrived problems, and really this is not useful at all. And like, there was a point 5 years ago in the community where we were all proving these sorts of things and we were super excited about them, and then we kind of all knew or realized their limitations. And maybe some of us regret writing those papers because then companies took them and misinterpreted them and said quantum machine learning is going to be incredible, and like the fine print got lost in everything. For more realistic problems, however, we have very good theory evidence that naive quantum methods won't do well. And so this is not looking so good. But really, actually, this is just an invitation to explore clever quantum methods. We know that if you just take a parameterized quantum circuit, a random one, like, you will not be able to learn well with this, and we can prove this. But this doesn't rule, like, but knowing what doesn't work is extremely helpful when you're trying to look for what could work. Because there's this theorem that says if you do this thing, it won't work. So whatever you do shouldn't do that. And what we have to do now is find the right architectures, the right sort of layouts of the parameterized quantum circuits with the right inductive biases for the specific problems that we want to solve. And here people have a lot of ideas. For instance, there's geometric quantum machine learning, which tries to incorporate symmetries into the circuits. And there's lots of other ideas. So even though we have this kind of evidence that there are some limitations, there's gaps there. And the truth is that the jury is out. Like, we really don't know whether there will or will not be advantages in this setting. And there's a lot of work to do there. Okay, so I've got 2 or 3 more slides, and let me kind of now advertise something that I'm kind of become a little bit obsessed with recently, which is, imagine quantum computing works. Like, could we trust it? And what does this mean? So imagine you're Alice, and you're interacting with some Bob, and you have a regular computer, you have your MacBook, and you interact with Google or IBM, and they claim they have a quantum computer. And now you pay them to solve some machine learning problem for you, and they send you the solution. Like, how can you trust them? Like, how do you know that they don't use just their like janky GPU and send you the solution? Like, maybe they don't even have a quantum computer. And importantly, like, this is hard because you can't solve the problem yourself. That's the whole premise, that like, you're paying them to solve something for you that you can't solve. And so what you need is a verification method. You need some like formal thing that allows you to verify that IBM indeed used the quantum computer the way they said they would. And so this is something I've worked on with some friends of mine, and we developed sort of rigorous, like provably correct interactive proof protocols for the verification of quantum machine learning. You can see it there, and when I did this, it kind of made me realize that this is just one example of a much, much, much more general set of problems. And basically, what it made me realize is that if you care about learning or machine learning, you should really care about cryptography. And let me try and motivate this to you. So cryptography is the branch of mathematics which allows us to not have to trust anyone. Every time you're involved in some interaction which involves trusting someone that you would not like to, you need a cryptographic protocol, either encryption for communication or like zero knowledge proofs if you don't want to reveal to them your knowledge. These are at the heart of blockchains. And so whenever you have to trust someone, you should turn to cryptography for a solution. But in modern machine learning, there are many, many, many situations, novel situations, which involve trust. And let me motivate some of these for you. Imagine you pay Google to run your training algorithm on their ultra fancy GPU. Like, how can you trust that they actually did those calculations on their fancy GPU? They could just be doing it on like a much less fancy GPU than you paid for. Ideally, you should demand a cryptographic certificate that they used the resource that you paid for. Or you pay OpenAI access to the latest version of ChatGPT. This is super expensive. You want the latest reasoning model. And then you make a query. How do you trust that they actually used the latest version to answer your query? Again, like, it's totally in their interest to not do this and just use a cheap model. Like, again, you should demand that there's a cryptographic protocol that allows them to prove to you that they used the resource that you paid for. Or imagine you ask ChatGPT a question like, is this molecule dangerous to humans? Again, it gives you an answer, and how can you trust that this is correct? Like, you shouldn't. And ideally, you would like to develop models that can themselves provide certificates of correctness. And then something we're all familiar with, you ask a student to write an essay, they submit it, it's really good. Like, how do you know that they wrote it and not ChatGPT? You have to trust them. These are all novel situations of trust, which we require cryptographic protocols. And the one nice thing is that we know that quantum cryptography is better than classical cryptography. So I haven't spoken about this, but cryptography is an area where quantum mechanics can help us a lot. And so this naturally asks, can we get cryptographic advantages in quantum machine learning? So even if we can't prove that quantum machine learning algorithms are faster or need less data, can we prove that they have cryptographic advantages, that they allow us to provide certificates that we've actually used this model, or certificates that the answer is correct? And this is something I'm very interested in. Okay, so the last 2 slides. Like you've seen, there's many, 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 many interesting questions. And here there is like a huge opportunity for you. Because addressing all of these challenges requires like a quantum-enabled generation of researchers. And learning quantum computing and interacting with quantum computers has really never been easier. So there are many companies that have open source software frameworks for quantum computing. And I really encourage you to take advantages of this opportunity. And this workshop's been organized by IBM, and they will here later give a tutorial in Qiskit, which is kind of one of the leading open source programming languages. And so there's some organization which tracks the usage of open source software frameworks in quantum computing. And this is kind of a graph of the usage by country. And unfortunately, like Africa ranks really low. Ghana is the first one at 0.9% of users, and then Nigeria, and then South Africa. Essentially, we have a really, really long way to go. And there are lots of initiatives like Quantum Leap Africa, the South African Quantum Technology Initiative, the Open Quantum Institute, the Unitary Foundation. There are many of them. And I like really encourage you to get involved and to, if you're interested in this, to reach out to those organizations. Lastly, if you're interested in these things, at Ames, we're building a research group in quantum computing. We have 2 PhD positions and a postdoc. And if this sounds interesting to you and you feel like this is the sort of thing you would like to do, you can come speak to me or also see the posters for these ads that are in that building where all the companies are based. Cool, thank you.
Awesome. Thank you so much, Ryan. So I really hope that you guys enjoyed the keynote from Ryan, and also is coming from a domain totally unrelated. A lot of this may seem foreign. I think the key thing is to remember that you need to find the language of quantum that speaks to you. And to facilitate this, we've really got 2 awesome presentations coming up, one by Nyase and then another by Yusra. And you will see that the content that we will present today, it will touch on similar concepts and technicalities, but they will be presented differently. So please just continue to absorb the information as much as possible and ask questions throughout. And quantum is really about not giving up. Understanding the technicalities, I think you really become lifelong learners when you decide to take on quantum computing. So thank you very much, Ryan. It's really been a fantastic talk, and I'll ask Nyasi to join us now.
I'm Ndebo Nyasi. I'm a research scientist at IBM Research Africa. I've been a research scientist there for about 2.5 years. And yeah, some of my background might be similar to you guys. For instance, I did my master's in data science at the University of Cape Town. I actually recently finished it. I'll be graduating soon. Yeah, and some of the things that we've been working on at IBM Research Africa, in particular in Johannesburg lab, is quantum computing, topological data analysis, and quantum machine learning. Right. Please do check out the package that we had released, I think, late last year on weighted gene topological data analysis. It's a data mining framework for genetic exploration where we use persistent homology to look at, how can I say this, gene co-expression networks. And I've introduced myself a little bit, but I also want to explain why I like quantum computing. And I really think it's a melting pot of interdisciplinary studies, right? For instance, you have complex numbers, linear algebra, quantum physics, classical physics, information theory, how do you represent units of information, signal processing, number theory, and ultimately for QML, quantum machine learning, right? And these kind of also form the backbone of a lot of AI machine learning models that we use to this day, right? So that's kind of the reason why I really like it. It brings a lot of these interdisciplinary studies into one melting pot where we can actually really try and solve new and novel problems. But enough about me, right? Perhaps you've Googled or used ChatGPT in this case and tried to understand what is a quantum computer? What are qubits, right? Perhaps maybe you've heard that qubits use both zeros and ones at the same time, right? Or perhaps you've heard that quantum computers will break RSA encryption, which formulates some of the cryptography security systems that our banks, our messaging apps, and the internet use. Or perhaps maybe you've heard that there are bigger, faster versions of high-performance computers, right? And today I hope to kind of like demystify some of these notions, these conceptions, and kind of get into a little bit of the mathematics and the crux of what ultimately is quantum computing, what problems we're trying to solve. So I wanted to go into some of the foundations of quantum mechanics, right? And why we actually need to utilize this methodology for simulating small atomic particles. So beforehand, physics was dominated by Newton's laws, Maxwell's electromagnetisms, but they did not scale to the subatomic level. Think of atoms, protons, neutrons, gluons, very small particles. With that being said, quantum mechanics is the branch of mathematics and physics that describe how matter and energy are represented or behave at the smallest scales. And unlike classical physics that we kind of live and breathe every single day, they kind of introduce a few radical new ideas that are counterintuitive to how we understand the world around us. For instance, matter and energy are quantized. They come in discrete packets. Particles can exist in superposition. And what does that even mean, right? How can a particle or something exist in multiple states at once? Or perhaps measurement affecting reality, right? Observing a quantum system, observing or measuring a quantum system collapses that quantum system into a definite state. What does that even mean conceptually, right? And what is measurement and observation? And also, particles can be entangled, meaning their states can be linked across space. But I do like this definition that's here at the bottom, where it says that quantum mechanics is a probabilistic theory of waves and particles. Now I'm going to go into some of the important experiments that form the foundation of quantum mechanics, and we're going to start with this double-slit experiment, right? So now pretend I have a paintball gun, and I want you guys to get involved, right? I have a paintball gun. There's a screen with two slits behind the paintball gun, and I'm shooting towards the screen behind with two slits. What do we expect to see if I put another screen at the back? Any takers? Cool. Yeah. Let me come to you, actually. Cool.
Thank you. Yeah, two lines of paint.
Yeah, 2 lines of paint. 2 lines of paint. Anyone want to give another answer? Okay, I think that's kind of the general answer that we expect to see, right? We expect to see the paintball bullets going through those 2 slits and 2 lines of paint, right? Now, what happens if we have a electron beam gun and we're shooting electrons? Remember those particles, those subatomic particles that we can't see with our naked eyes. What do we expect to see? Any takers? Cool. Yeah? You could just... Oh, okay, cool. Awesome.
My name is George. We expect to see waves. Waves like...
waves?
Yes, waves.
Cool, cool. That's an interesting answer, right? But that's very counterintuitive to how we experience everyday life, right? Is there another answer? Maybe we expect to see a similar pattern to the paintball gun, right? 2 lines or electron beam gun bullets that are sprayed against the screen behind, right? But actually, George, you were right. Sorry. Yeah, there we go. Actually, George, you were right. We see this interference pattern, right, which suggests to us that maybe particles may have wave-like properties, right? Wave-like properties meaning They may have frequency, amplitudes, phase associated with those particles themselves. The way I like to think of it is kind of like an actual wave of water going through these two slits and having constructive and deconstructive interference when the phases match up within the signals themselves. Kind of like this image here. Now, I don't believe that because that's very counterintuitive to how we experience everyday life, right? I don't believe that, so now I'm going to measure. I'm going to observe what is actually happening, right? And what do we expect to see when I'm actually observing and not just measuring the output itself? Any takers? Apparently you get merch if you answer. Okay, a few hands went up. Cool, yes.
Yeah, so I think they get 2 lines.
2 lines. So again, very counterintuitive because we just saw previously that they were waves, right? But when we observe, right, we see 2 lines as the young gentleman got correct, right? Similar to the paintball guns hitting the back of the screen. Okay. No. This doesn't really make sense, right? Let's say I'm not looking, I shoot the electron beam gun, similar experiment, but there's no sensors attached to the screen behind, right? What do we expect to see? We see the interference pattern again, right? Suggesting the wave-like properties, but also suggesting something more subtle, that measurement is affecting reality itself, right? Measurement collapses the wave-like properties of the particle itself into a localized object where we can measure the position. Speaking about position, we have Heisenberg's uncertainty principle, right? I won't go too much into detail on this, but the more precisely we try to determine a particle's location or position, the less precisely we know about its momentum. And we could think of this as its momentum being a collection of frequencies associated with the particle itself. So we kind of abstract away from the wave-like properties and measure a particle in a position. So for instance, if you're trying to, how can I say this, link between the 2 experiments, Heisenberg's uncertainty principle and also the double-slit experiment, if you observe a particle that goes through the slit, you destroy that interference pattern and you measure the property of position rather than abstracting away from the property of the wave-like behaviors. Now we also have Schrodinger's cat. I just want to also get a show of hands. Who has heard of Schrodinger's cat? Okay, let's say, I would say like 20% of you. Okay, cool, Schrodinger's cat. Cool, I'm glad to be explaining it to new people, but Schrodinger's cat is kind of like, it was created by this German scientist called Schrodinger, where he kind of gave this thought experiment or this analogy to kind of explain these unintuitive behaviors of quantum mechanics. In this case, we have a cat that's in a box, and this box is sealed with some poison that has a 50% probability of killing the cat and a 50% probability of not killing the cat, right? And how I'd like to think of modeling in quantum mechanics is before we measure, we can actually model this cat in a superposition, so existing in 2 positions at once, whether it's dead and alive, with an associated probability or amplitude associated with those definite states, right? With that being said, it doesn't necessarily make sense, and it kind of demonstrates some of the intuitiveness and kind of also the steep learning curve associated with quantum computing as well as quantum physics. But hopefully today we'll kind of get through some of the mathematics and hopefully it makes more sense. So I wouldn't worry too much about this experiment yet. But coming from an AI and data science background, I'd like to also say that the linear algebra associated with physics and mathematics is the same associated with machine learning. And I say this because when I think of vectors and matrices from my background, I always think of data frames, pandas, NumPy arrays, right? And these are vectors, in particular, one-dimensional arrays, for instance. And we also have matrices that form data sets with features and observations, rows and columns, for instance, right? But I do want to say that even though physics has a different idea, or for instance, it'll give you a different definition of what a vector and matrices are, they're all one and the same. And I think sometimes the steep learning curve between learning quantum mechanics, especially for us computer scientists, is associated with this difference in the language and notation that they represent linear algebra objects. Cool. Now I just want to get into the limitation of bits, right? And bits have done so well for us, right? They're binary units where we can have zeros and ones. And if you add up millions of transistors, we can do really, really amazing things computationally. But then again, simulating nature, it's not binary, right? There's in-betweens, and the fundamental unit of information, can we actually add some more units to kind of express in higher detail these units of information? So we have a bit which is a unit of information between 0 and 1. But we also have our classical logic gates that are a set of gates associated to perform operations with these bits, right? But for quantum now, we have a qubit, which is also a unit of information. And we also have quantum circuits associated with the qubits that manipulate the qubit themselves. Now, on the right here, I put some famous gates for quantum. We have the X gate, Y gate. We have phase transformation gates, control NOT gates, that sometimes they also form or do similar things to our classical logic gates, but they are matrices themselves. And they have certain properties associated with those matrices that preserve the state's probability through the unit vectors and through the normalization of Born's rule. So Born's rule is when you square the amplitudes of associated states, you can sum up the probabilities of a unit of information themselves. So now we have a qubit, right? And we have a part that's associated in the 0 state. Now, firstly, I think I should mention is that this is a ket, right? And I just want to ask in the room, who has heard of Bra-Ket notation? Notation, okay. There's a few people. So this notation might actually look unfamiliar to a lot of you, right? But what I would like to say is that these two are unit vectors in different directions. So they form an orthogonal basis, right? So we have a unit vector 0, which is 1, 0. So we go horizontally on the axis, on the x-axis, 1 unit to, I guess, the right, and 0 units up and down, right? So it's in the middle when we're looking at it from the perspective of the y-axis, right? And then we have a unit vector 1, which is in a completely different direction, which has a 1 in the vertical plane and 0 in the horizontal plane, right? So we're associating probability amplitudes or amplitudes associated with different basis states. And this is how we can represent 1 unit of information as 2 pieces of information through a qubit. And when we utilize these probability amplitudes, we can normalize them and extract the probability that the bit, once we measure, once we observe the state of, as we observe the state of the bit, we can associate them with probabilities associated with the 0 state and the 1 state. I hope that makes sense. And please also feel free to stop me if you have any questions. Again, so we have the 0 state and the 1 state, where they're just column vectors. So this notation is called DRAS notation, and it's to symbolize a column vector. A column vector where the top position is the x-axis, the bottom position is the y-axis. So we have two states, the 0 state, the 1 state, that form, again, that orthonormal basis. And we can use this to write any vector in C2. So we have amplitudes, or you can think of them as coefficients that are associated with each state, right? We have coefficient A and coefficient B here, associated with each state. Once you square them, you get the probability of the state being in state 0 and the probability of the state being in state 1, and then you sample from that probability bit string. Now we also have superposition, and we use superposition to create a quantum state that is both a combination of the 0 state and the 1 state. And if you think about it and compare it to a classical bit, we are encoding amplitudes associated with each basis state within 1 unit of information, as compared to a binary unit of information which we have on our classical computers. But on our classical computers, again, they scale really well with the millions and millions of transistors that we have. And this is the idea of superposition, right? And if I were to relate it back to the cat, right, Schrodinger's cat, the cat that is both dead and alive, right? We have a amplitude that is associated with the cat being alive, and an amplitude associated with the cat being dead, or a coefficient associated with the cat being alive, and a coefficient with the, associated with the cat being dead. And we can use this unit of information to model quite interesting things as compared to just a binary unit of information. Again, this is called a block sphere, where we can represent in C2 the kind of like the positions that you can access within this qubit, this information unit, right? And we could have different transformations, different phase transformations, different amplitude transformations, depending on how we use our quantum gates associated with the bit itself. Again, just to kind of put everything all together, so this is psi, and it's just a wave function, or you could think of it just as a function, which has an amplitude associated, again, with the 0 state and an amplitude associated with the 1 state, right? These amplitudes are in are complex numbers, right? And when we sum up and square these, we get the magnitude of the bit itself, the qubit itself. And these sum up to 1, and they have probability distributions associated with both states. Cool. We can also represent them in polar form as well. So we can use these thetas to rotate around this block sphere, accessing different points that we want to encode in our unit of information. Oh, sorry. So now I just want to show you some of the effects on gates, and there's also a nice tool on the internet that I can quickly also show you guys. But we have an X gate, which is a matrix that is 0, 1, 0, 1, right? And when we act upon a qubit of information, we perform a bit flip. So similar, you would use a classical gate to perform a bit flip. We can do so as well using a qubit of information. So again, when we perform a bit flip, we can go from 0 to 1 or 1 to 0. And again, this is a very special gate in quantum mechanics and quantum computing. It's called the Hadamard gate. And we can utilize this gate to put a initial qubit state into superposition, right? So think of this as associating the probability amplitudes with the 0 state at 0.5 and associating the probability of the 1 state at 0.5. So there's about a 50% chance that once you measure, it will be associated with the outcome will be the 0 state or the 1 state. Cool, and now we also have this phenomenon called entanglement. I won't go into too much detail on entanglement. I know Einstein called it spooky action at a distance. So it is kind of counterintuitive, but you could think of these states being linked in some sort of way depending on how you prepare your states. And then we also have interference, which allows us to increase the probability of getting the right answer and the wrong answer. So think about the waves that we saw when we were looking at the double-slit experiment, for instance, right? We saw that the waves were propagating against the screen behind it, right? Creating this interference pattern. So if we have phases that amplitude and propagate with each other, with the associated amplitude, we can kind of model our questions in such a way that we increase the probability or increase the amplitudes associated with the states with the correct state as opposed to the incorrect state. And then again, we have measurement, right? Measurement where we're forcing the qubit state into a particular state, into a particular basis vector. Again, we can associate them with different amplitudes, thus having probabilities associated with different basis states. For instance, the example below. And I just want to thank you guys as well for listening. I think Yusra is going to come next, and yeah, I hope that was informative.
Okay, welcome back, everybody. Thank you so much for joining us for the second part of the QML4Africa workshop. If you are missing colleagues and friends, please do message them and let them know we are starting now. As you know, our program is packed, and we want to get to the nice, busy things, right? So just a quick change in the schedule. What we have decided is to move the talks for the posters, the invited talks, to after the panel discussion, just so that we can give enough time for Yusra to take us again through understanding quantum machine learning and the notation. And I think you'll also see a little bit of the quantum composer and how the gates change the rotation of the qubits, right? So I think that's quite important. We'll also go into the practical component. And as I mentioned, we are quite tight on time, so we have 1 hour to get through this. And as you can see, we've set up for a panel. So we've actually collaborated with the Compute workshop, which is happening simultaneously next door. And they will be coming over to this venue and setting up here and moderating the panel on HPC and HPC for Africa. So I think it will be quite cool to have all of you present and hear the contributions from that perspective. Petra Florizon, who is our global sales leader for IBM Quantum, she's also on the panel. So to understand, the landscape of quantum in Africa, ask all your questions, please do. So that's pretty much the plan. I'm going to hand over to Yusra, who will introduce herself. We'll do the practical. We will then have the panel. And just after that, we'll give some time for the talks, and then for anything going forward. So please, let's welcome Yusra.
So hello everyone, I hope you're doing well. Thank you so much for coming to the QML workshop. I'm so happy to see a lot of the faces that attended the lecture last day here. That's quite interesting. That means that what we're doing or what we're presenting is something that interests you. And I think that most of the questions that you'll have is how can we as machine learning engineers dive into quantum computing. So I'll just introduce briefly myself. I'm a quantum computing researcher at INSA Lyon in France. I work basically on the development of quantum algorithms for fault-tolerant quantum computers. And I'm founder of Quantum-Africa, so if you're interested, just scan the QR code to go to the website of Quantum-Africa. And later on, you're going to hear more about this from Stephanie. So I think you had a lot of questions in mind about quantum computing, like the fact that these qubits can exist in multiple states at the same time, and that these qubits, they can allow you to perform more complex computations. So I just will refer again to the three main phenomena that we usually take from quantum physics and quantum mechanics to project into like quantum computing. The first one is the superposition, as Niasi have explained, is the fact that the particle or the atom can exist in multiple states at the same time. So this will allow us to explore more potential solutions. The second phenomena is the entanglement. So yeah, let's back to the quantum phenomena. So we talked about superposition, the fact that the quantum particle or atom can exist in multiple states at the same time. And then we have another phenomena which is called the entanglement. So two quantum particles are entangled. By saying entangled, we mean like if I have a particle here and another particle in the United States, if I'm revealing the information in my particle, the other one is going to be revealed with like no communication basically between these two particles. And then we have the interference, the fact that if you want to get, for example, to solve this maze, so if you want to do that on a classical machine or a classical computer, so what you're going to do is you'll be exploring a lot of solutions that they say sequentially. So we'll be checking whether the first path will lead you to escaping this maze, if not the second path, if not like the third path, until you explore the whole maze. But in quantum machine, you're gonna put this maze in a superposition state where you tell it sort of like explore all the search space at once, and then using the entanglement and the interference, all the wrong ways or the wrong paths will cancel up so that you'll have the right path on one shoot measurement. So it's like one measurement that will allow you to solve this maze using the Grover search algorithm that exists. So if you just Google the Grover search, you'll be able to see it. So just to give you like an overview about the growth in quantum algorithms. So in like between 2024 and 2025, there is more than 6,000 publications on arXiv about quantum machine learning. So the field is really evolving so fast. And as Dr. Ryan mentioned, there is a lot of questions, a lot of open questions, and a big exchange back and forth between the quantum community and the machine learning community. How can we use machine learning to benefit quantum computing, and how can quantum computing and leveraging the quantum phenomena can help us to solve some unsolvable problems in machine learning. So there is like a lot of amazing publications at NeurIPS, for example, last year about quantum machine learning. If you're interested, you can also check them. One like interesting example that I always want to refer to is this work done by the University of Technology in Sydney, where they had like a proof of concept of the implementation of GPT on a quantum computer. So here's like the link for this publication. Theoretically speaking, when we talk about encoding more data on quantum computers, we say like we can encode the whole GPT-3 data, which is 175 billion parameter on 38 qubits, but this is far from reality, because the reality that we have error in these qubits. So for one qubit, it will take us like more than 200 or 300 other qubits to be able to mitigate the error in the algorithm. So this is just like a quite cool example if you want to see how they approached the GPT architecture from a quantum perspective. Now talking a little bit about quantum machine learning. So there is several like definitions of quantum machine learning in the literature. I always see it as the intersection of the math for machine learning and then the compute or the computing resources that we get from the classical computing. So one of the famous like definitions of quantum machine learning is that it is the study of the algorithms that can be run on quantum computers, but designed to learn like patterns and leverage the data using the quantum phenomena like superposition, entanglement, and interference to gain a computational advantage. One of the open questions is the quantum advantage. So we cannot claim right now that there is a quantum advantage when we talk about quantum machine learning, but there are some challenges that exist in the classical machine learning that potentially the power of quantum computers can be able to solve these challenges. One of them is the large feature spaces that we have in classical machine learning. So with the fact that we have superposition that will allow us to position the state of the qubits to explore a lot of like possibilities at the same time, this will allow us to explore these large feature spaces more efficiently. We also have high dimensional data, and then once embedding this data into Hilbert spaces, and we're going to see that later on in the prac, you'll be able to capture more information within this data, and this will allow us to see somehow a potential advantage in quantum machine learning. And then we have, like, for example, the slow kernel evaluation in classical machine learning, where we have like another version of this in learning, which is the kernel method. So there are several kernel methods that are faster and also more secure when it comes to interchanging the data between the different kernels. And also we have like the optimization. So we usually tend to use quantum annealing, QAUA, and VQEs, which are like algorithms for quantum optimization to optimize over the loss function in classical machine learning models. So these just few challenges that we have in classical machine learning that we might see the potential of using quantum machine learning in them. And now let's move to the QML use cases. So there are a lot of applications. As I said, like 6,000 papers, a lot of things is going on there. For example, in healthcare and medical imaging, I always refer to this example more specifically, the quantum Hadamard edge detection algorithm as one of the best algorithms nowadays to compute the gradient in like O1 complexity independent from the number of features in your data set. So this is like a novel algorithm that came from a sort of quantum mindset to be able to solve this like gradient problem. There is also like the use of QML in drug discovery and molecular simulations. As we know, there are a lot of problems in chemistry and in drug discovery. These problems, naturally, they are quantum problems that even with the best like classical model out there, we are not sure that we're getting the best out of this. Let's say simulating these interactions between the molecules, or just trying to understand the behaviors of these, let's say, bacteria or viruses like the coronavirus. So quantum machine learning allows us to have versions of these models and to simulate these molecular interaction in better ways. So this is like one of the interesting papers about quantum machine learning predicting ADMI tox properties in drug discoveries, and they are showing a real advantage in using quantum machine learning algorithms here over classical algorithms. We have also the use of QML for finance and risk analysis. So there is the portfolio optimization as an NP-hard optimization problem, where we can see clearly the advantage of using quantum computing in solving optimization problems somehow faster than the classical computers. Still, with limited number of qubits, we are somehow limited. And then for sustainability and climate change, so there is a lot of proposed work, a lot of frameworks for using QML, and mostly quantum optimization in energy grid distribution, in energy optimization. There is this interesting work about quantum computing and quantum artificial intelligence for renewable and sustainable energy. So there is a whole pipeline on how to get the most out of the quantum AI in building like a framework that can allow us to produce more energy. Now, for the types of QML algorithms, I always prefer to classify them into 3 categories. So the first one is the quantum-enhanced ML. That means we are using quantum systems to improve the existing machine learning. And here we have like different algorithms. One of them is the VQC that Dr. Ryan had presented before. One of them is like variants of the existing classical machine learning algorithms. Like, for example, we have the classical SVM, but we have also like a version of the quantum SVM. We have quantum neural networks, quantum K-mean clustering, and quantum tensor networks. The second category is using classical machine learning for quantum tasks. So here we can use like classical machine learning to predict the outcome from quantum circuits. We can use it also to optimize and control over the like the quantum algorithm or the quantum circuit, because you know, like the more the algorithm gets bigger, the more noisy it gets. So here there are like several frameworks existing in the literature that allow us to simplify these like circuits using deep learning models. And then we have also the error correction. So the famous example of the alpha qubits. So it's like a framework created by Google DeepMind and Google Quantum AI recently in 2025, where they were able to reach below threshold error in the superconducting qubits that they have. So this is like a full AI and not quantum framework, but is used for quantum computing. And that's why you have a chance, if you're interested in quantum computing, to use what you know in the existing like classical machine learning to solve these problems. And then we have the hybrid models. Honestly, it's not the best way to do quantum computing with the hybrid models. I'm not a fan of them, but it's more of like we're creating a sort of model where you have some quantum layers and classical layers, and we try to prove that there is a sort of advantage of using this. But in most of the times, like most of the papers that you find about quantum machine learning are like people trying different variants of Q-GANs and quantum NLP and like some neural network with few layers, like quantum layers and few classical layers, to be able to see whether we can really capture more important information from the data. Okay, so some research area in quantum machine learning that also might interest you is the mathematical foundation of quantum machine learning. I know if there are people here from Mila are really interested in the mathematical foundation of QML. There is also the causality in QML for people working in classical causality. It's so interesting to read about what you can do using quantum computing when it comes to causality in machine learning. And then we have explainability. So we tend to say that probably the quantum machine learning models are more explainable, but it's also like a very open research area where you can maybe be interested and jump in it. Now, let me give you a small introduction to the QML pipeline. So this is like one of the basic pipelines in quantum machine learning that allow us to build quantum machine learning models from samples of data, like small amounts of data. So the process goes as follows. We have a classical data space, so like normal data sets, and we do some quantum embedding to embed this data into quantum Hilbert space. So there is a whole phase of pre-processing where we pre-process this classical data to turn it into quantum data that we can later on build on like the ansatz circuit or the model, and then do some post-processing to get the outcome of this model at the end. When it comes to quantum data encoding or creating feature maps, as we tend to, I'd say it in quantum way. So we say, instead of saying encoding data, we always say creating feature maps. So we have three actually more ways of encoding data, but these are like the three main ways. The first one is the basic encoding. So we just represent each classical bit as a qubit state, either like state 0 or 1. We have the angular encoding, where we encode features into rotation angles, as presented previously by Dr. Ryan. So we can like do certain rotations, because you know, like the structure of the qubits is in three-dimensional space. You have the x, the y, and z, and you can do these rotations over the x, y, and z using the R gates, which are the rotational gates, and you can encode the data, the classical data, and transform it to quantum data. And then you have the amplitude encoding. So it's about like encoding the entire normalized vector into amplitudes of quantum states. And this is costly most of the time, so we tend always to use angular encoding when we want to build like some small QML models. So quantum computers, they naturally map the data into Hilbert spaces, and quantum computers are known of like exploring Hilbert spaces efficiently. That means they can perform the embeddings of the data more efficiently, when theoretically speaking, when compared to classical machine learning. So you can just see this example. So the original data in like two-dimensional space, and then the embedded data in a Hilbert space, which is like three-dimensional space. And you can imagine, when it comes to molecular interaction, how much information you can get when presenting your data in this way. We have also the quantum models representation. So like instead of using neurons and weights and layers, we use PQCs, or parameterized quantum circuits. So we have basically this idea of unitary gates, and the unitary gate has a certain weight, which is the theta weight, and then the whole process is like we try to optimize over this weight using classical optimizer or quantum optimizer, update the weight every time so that we can get the most out of the quantum model. For the quantum learning process, so it's a forward pass. We just encode the classical input into quantum states, apply parameterized circuits, and then measure the expected values and output the probability distribution. For the training loop, we basically define a loss function similar to classical machine learning, and then we try to optimize over this loss function. One of the best ways to do that is to try to write the cost function as a QUBO, quadratic and constrained binary optimization, and then try to solve this QUBO as a quantum optimization problem using one of the available like quantum hardware, for example, D-Wave or InfinityQ. And then we also can calculate the gradient using the parameter shift rule, but like we cannot really avoid backpropagation in this way, because it's a little bit costly when it comes to creating, because we need to create more in-depth circuits, and then we need more qubits. So this is, theoretically speaking, we can, but in terms of the current state of the hardware, it's a little bit tricky. Now, to train QML models, so we have the first variant of like the, let's say, one of the famous QML models, which is the VQC, the Variational Quantum Circuit. It's made for NISQ era, like the noisy intermediate scale quantum computers, where you have just to optimize over that theta, and then you have the problem of the vanishing gradient, and basically this is not the best way to do quantum machine learning. And then you have the quantum kernels. So like quantum kernels, you can actually prove some advantage, but it's not the real advantage of when we speak of it in terms of accuracy or like results from the model, but more in terms of how can you manipulate this data in a secure way. So there is like the version of the quantum kernels mostly applied into quantum SVMs. And then we also have the quantum generative models. There are several, like as I mentioned before, several ways to do that, but there is like one interesting work which is going like right now by a company called Quantinum, where they are trying to build the first Gen Q AI, say like a generative AI or quantum LLM. So there is a lot of talking about their ambitious projects, but it's also worth to to see it. And then we have the fully quantum training, or the future of quantum machine learning, I would say, algorithms like quantum backpropagation, which I said like it's not possible on the actual hardware. So for the prac for today, after Niasi will take you over how you manipulate quantum circuits, how can you like code these gates and then access the quantum simulator or the real quantum hardware from IBM to be able to do these like operations. We will have a prac on how can you build a quantum classifier. So I prepared for you 2 versions. Hopefully we'll have the time to go through all of them. Otherwise I can share with you the code, but we will understand how can we build a quantum classifier from scratch. So I'll just go through this slide quickly and then we'll proceed with the prac. So the idea is literally similar to the previous circuits that I showed you, where we have like a data set. We do the pre-processing, we transform this data set into a feature map, and then we create our variational circuit. We do the measurement, and then we keep optimizing and updating the theta weights so that we can get the most out of our model. For this example, I choose to do it on the Iris dataset and the MNIST dataset for 2 digits. So yeah, thank you.
On time, but I think just to wrap it up, we clearly know that there's been a major evolution of computers. Just thinking about where I was about, well, a couple of years back, struggling with an Excel spreadsheet that just wouldn't open up a large sheet of data and crashing on me, and thinking about where we are today and being able to analyze huge data sets. And yeah, I think the possibilities are really endless, as we know that we are generating large amounts of data moving forward, and especially in domains such as climate and healthcare, you know, you need large data sets to even be able to derive statistically meaningful results. So the need for high performance computers and quantum computers essentially is there, and I think we are very excited to see how to grow the community and where we are going. So are quantum computers real? Yes, they are. They exist in multiple forms around the world, and you can access them today. And part of today is hopefully that you will make your IBM Quantum account and start having some access to the qubits that are available. And yeah, I think this is really important for you to have that hands-on experience. I think I just want to end off with 2 or 3 slides. What's really important for everyone to know is that we are not talking about quantum computers taking over the world and replacing classical computers. That's not the whole point of this, right? It's about finding the synergy and the need for quantum computers. So 1 + 1 and many other computations you can perform classically, that is perfectly fine. But there are some parts of experiments that are just too hard for us to perform on a classical computer, and it will take thousands and thousands of years to get the result. So if we are able to, we need to take that data set, have, as Ryan was saying, really fully understand the domain, understand the problem we are trying to tackle, pair that up with the correct algorithm, and push that onto quantum workflows where we can get the results much faster. Obviously, the goal is in terms of working towards a high accuracy and reproducibility of the result. That is all part of the mission. So it's really about identifying the part of a workflow that goes classically and part of the workflow that goes on a quantum machine, and creating that harmony between the two. I like to think of it as a dance. So to that point, a lot of the work that we are doing as IBM moving forward, or as what we are doing today, is integrating your classical compute with your GPUs, your strongest and most powerful classical computers with quantum computers. So it's, as I said, about the synergy, and the panel that is happening at 1:30 will touch on a lot of that. So just 2 more slides. How do you get involved? Now that you've had these foundations, how do you learn more? Where do you go from here? We've recently completed the 2025 Qiskit Global Summer School. There was really, I think, the largest number of attendees, and this is where you can go and have access to really good materials to get started. All the videos have been released on YouTube, so please do go and check it out and share it with your students, with your friends, with your colleagues, so that they can also have access. The next thing is the Qiskit Fall Fest. So I think the applications for this have closed, but please check in with your communities if they have submitted. If you still are interested, reach out to IBM Quantum and see if your communities can get involved. These are events that, whether it's a workshop or a mentorship session or just a discussion, it takes on various forms. It's about bringing communities together to talk about the technology and talk about the impact and the research that can be done locally. So with this, you can have support from IBM. And last but not least, we tried to very quickly put together a slide of all the things that are going on. I know that we are missing some events, but we host meetups in hybrid form, online and in person at the IBM Research Lab in Johannesburg. We've also got, obviously, like the Africa Quantum Consortium, amazing organization as well. They have weekly meetups every Friday, so there's something for everyone. And I feel like kind of we don't have an excuse at this point in terms of how to get involved and how to gain the knowledge, right? So at this point, I'm really going to hand over to Nyase and Yusra, and I'll also be running around to help you guys to get set up for the practical. Awesome. Okay.
Idea of an example.
Are you all able to scan the QR code? So you just have to scan it and open it up in your PCs. Just please let us know if you scan the QR code so that we can move on to the Quantum Composer.
Cool, awesome. I'm going to assume that everyone has signed in. Cool, this is a cool tool from IBM Quantum where we've prepared like a few qubit states, and we're going to use some quantum gates to try and manipulate those qubit states as well. Please do ask a friend if you had not signed the scan the QR code as well. Yeah, so what's also nice about this tool is that you also get the code that you also get the code associated with the qubit manipulations on the side. So if you want to set this up in your Python environment, you can do so as well. So the first thing I think we can do, we're going to probably use the most popular gate, which is the Hadamard gate, which puts the qubit into superposition. So as remember, superposition is a linear combination of states, and then we're just going to drag and drop this Hadamard gate. And then what do we see here when we output the probability distribution? We see that the probability distribution between state, sorry, I can't see that, between state 000 and state 0001 becomes 50% probability. So please do take some time and look at the tool itself. There's multiple gates having to do with amplifying frequencies, phase transformations, rotation gates around the qubit themselves. Yeah, and on the side there, as mentioned before, you do get a output of the code itself so that you can run on Python. And then there's also the block sphere manipulations that you guys can see. Yeah, so I think we're going to start with the practical, where we're going to explore some code. And I hope you guys are excited, because we'll kind of go through some of the code in just a moment.
Okay. So basically this tool is a sort of cute way to visualize quantum circuits, because you can like add more gates and build more complex circuits, and even create the VQC that we will be coding with Python using this tool. So it's more like a visual tool that will allow you to see the block sphere, you rotate it, you see the distribution and the code of the circuits. So let's just try to fix the error.
Okay, cool. Just show of hands who's able to access the Git repo. Okay, cool, awesome. There's some getting started code where we'll kind of navigate through the basics of quantum gates and quantum circuits. We just showed you the IBM Composer tool where we can explore the block sphere and visually add gates towards manipulating qubits. And yeah, I did also include a requirements.txt file, and the README should have some notes onto how to pip install all the packages required for the repo session and practical session now. Cool. We're going to start going around helping people set up their code, set up their libraries, and
if you facing any technical issues, we'll be around, and then we'll check the code with you. So just go over the notebook, and then creates a quantum bit, I'd say, and generate superposition. So the first thing to do is to import Qiskit. We import the component of quantum circuit and the transpiler. And then we import as well the IR simulator of IBM. This is where you're gonna run your code. And then the Qiskit visualization to plot these circuits so that you can see the circuits in front of you. So the first thing is to build the circuits. So we have a 1 qubit circuit that had the measurement. So this is how you can initiate the circuit. So just QC equal quantum circuit of 1. And then you're gonna add the gate, which is the Hadamard gate, H, and then measure this simple circuit. And then the next step is to initialize the IR simulator and to run or to transpile the circuit and run this circuit on the simulator. So the results are here, and here we get the count, and this is the measurement count. So we have 497 measurement results of getting 0 and 572 or 27, sorry, count of getting 1. So here, what you get from this exercise is that the superposition does allow you to get equal probabilities, but it does not give you the same output of the measurement by having 500 and 500. All right, so are you all cool with the first exercise of building the Hello quantum circuit? I'm just doing some temperature check. How many of you is able to create the first circuit? Okay. Cool. Nice. So the second exercise is to generate the GHZ state, which is the Greenberg-Horn-Zeilinger state. So it has 3 qubits, 3 maximally entangled qubits to characterize the bell state. So this is like the GHZ state. It has 3 qubits. So the first 3 qubits on state 0 plus the state of the 3 qubits on state 1 divided by square root of 2. So to do that, we need first to apply the Hadamard gate to the first qubit, which is qubit 0, put it in a superposition. So this is a sort of exercise that you have to implement yourselves based on the first exercise that I showed you. So we have a circuit with 3 qubits. The first thing to build this state is to apply the Hadamard gate on the qubit 0 and then put it in a superposition. That means you're just gonna link the first qubit to Hadamard gate, and then you apply the C-note gate between the qubits 0 and 1, and the C-note gate between the qubit 1 and 2, and then you'll get the GHZ state. The name of the C-note gate, even in Qiskit, is C-note. So you just have to type C-note, and then you will get the C-note gate. And then the second step is to optimize this state and transpile it. So we have like limited the action only here between the qubits 0 and 1 and 2 and 0, but there is no entanglement between qubit 1 and 2. So we can introduce these constraints to the transpiler using the transpile function and run these circuits. So here you just have to plot the circuit layout so that you can see the circuits and then execute it on the simulator, the IR simulator. So one thing to take into consideration is that you can also execute the same circuit on the real quantum hardware. You just have to create an account at IBM Quantum and then get your IPI token and put it inside the code and then run the cell. So it will connect your notebook to the IBM hardware. You just have so to get the API key, you just have to create an account in IBM Quantum, and then it will allow you to see your API token and use it to run the code. Let me just guys, just a clarification. So there is the IBM Composer, the like the website where you can visualize the circuits. And there is the IBM Quantum platform where you need to sign in to get your IPI token and then get access to the backend of and run the code. So there are two different platforms. So for the last, I think the last cell, you need to get access to the backend. You just have to create an account in IBM Quantum and then go to your profiles and you'll see the IPI token. Just copy paste it in the cell. So if you are wondering where to post or to use the IPI token, so you just have to import the sampler from the IBM Qiskit runtime, and then you have to initialize the Qiskit run service, and then here where you put the IBM token, the API, and then you can create a service, and then the service is going to be the Qiskit runtime service, and you can access the backend. So it depends on the availability, but you'll be able to access the backend for a couple of minutes. And then instead of you running on the IR simulator, here the sampler is going to be the hardware that you're going to use to run the circuits, the QC circuit that you'll be creating. So this is just in case if you want to do that on the real quantum hardware. So can I have your attention again so that we can go over building the VQC? And again, you'll find the code on the repo that we shared with you. So the first architecture of the VQC is similar to all the previous quantum circuits that we have introduced. So as I told you, we have the data set, the classical one. We do the pre-processing to transform the data from a classical data to a quantum data, create the feature map, the variational circuits, do the measurements, set up our cost function, and then try to optimize over the cost function and update it several times so that you can get the best result of your model. So the task here is a tiny task. So the dataset that we are using is a binary classification with 80 training points or data points. So the dataset is the make classification from scikit-learn. We need to do some pre-processing for the data just to normalize it so that it can be compatible with the quantum output. So all the labels should be converted to -1 and 1. And then the architecture of the VQC here is that we will need two classical features, and then we will do angle encoding, as I showed you before. So the angle encoding, we're gonna rotate the qubits on the different rotational gates based on the angles. And then we will define our PQC with a multi-layer circuit. We will do the angle embedding with rotation around the y-axis. And then the main, like the whole model is built on 2 qubits only. So as you see, this is like the architecture, and I think you can also open the code to see what I'm talking about here. So just try to follow up with the code on Colab. So we did, so we got the 2 qubits, we did the angle embedding, and then we did the rotations on the X, the Y, and the Z, and then we had some entanglement between the 2 qubits, and then we did the rotation again, and then we did the entanglement again, and this is our quantum circuit. At the end, we measured only the first qubit, which is the 0 qubit that will allow us to get the classification results. So this is the mathematical formulation for the loss function, and the training is using gradient descent on penny lane. So if you run the notebook, you'll get really impressive results with only 2 qubits. So the accuracy is almost 90%, depending on the depth of your circuit. So you can also recreate the circuit with more qubits. So for this example, I only used 2 qubits, but you can make the circuit more complex, adding more gates, encoding the data in more proper ways so that you can get the most out of it. So this is the first notebook shared with you, and basically it's on the classification or binary classification dataset. There is also the second notebook, which is also about building VQC, or variational quantum classifier, on the iris dataset. So this is a more concrete example. The dataset is big. We have 10,000 data points, and then we're going to create a more complex circuit. But what is interesting is that the circuit that will be created needs only 4 qubits instead of thousands or millions of bits to be able to do this like classification for the iris dataset. You will see that the accuracy is not comparable to the classical model. So the classical model outperformed the quantum model. But when we talk about the training time and then the hardware resources we use to get this accuracy, we are in a really reasonable range. So you can go through the notebook because I think it's time for the panel right now. If you have any questions, feel free to ask us or just like contact us in our emails or LinkedIn's. We are always happy to answer your questions, and then let us know if you have any like difficulties accessing either the IBM Quantum or the code that we provided. Thank you so much, and enjoy the panel.
Yeah, thanks very much. And yeah, like, so a few of us are joining this quantum workshop from the compute workshop. And thank you very much to IBM Research for this collaboration. So for now, I would like to invite the panelists from the compute workshop, including Petra from IBM Research. We have Kofi from Mozilla, Eugenie from GSMA, to come up to the stage and take a seat, please. Yeah, and then who are we missing? We have Cassava, Robert. Please join us. Yeah, give them a round of applause, please. Yeah, so how we're going to organize this a bit is, so from the compute conversation before, we were delving into multiple demos, but also right before we were looking at how to bridge the AI compute divide, looking at the investment numbers, the key actors, and also asking the question, who benefits? And I think that this is also where we have individuals from two foundations and also two very critical private sector actor here. So I would like to open the floor for Petra, and then we can kind of go across where if each of you can tell us a bit about yourself and also the work that you do for the crowd here who may not know, and then also say a bit briefly about how your organization is engaged in compute activities on the ground in Africa. Yes, thanks.
All right. Hi everybody. Really happy to be here at Indaba. First time, so really impressed. Who am I? I'm Petra Florizone. I am working at IBM. I'm part of IBM Research, and I'm here with some of my colleagues who helped and supported with the workshop earlier today. What is IBM Research? You probably know IBM as hardware, software, whatever. But we also have a very large research department. We have departments in labs in US, in Europe, in Switzerland, in Israel, in Brazil, but also in Africa. We have in Kenya a research lab and in South Africa. So very proud of that. My job specifically, I am working in IBM Quantum. That's not me. Since this morning, you know all about quantum, I guess. But quantum is really something where we're focusing on the technology part, because we need to have those quantum computers to be able to really make something, become something useful. But on the other hand, we're also investing hugely in training, skills building, building the communities, and also that is something that we're doing on the ground with the teams here on the ground. We have somebody even present from Skills Build, who helps with learning. Very important, because what can you do with quantum computers if you don't have the skills, right? And this community building also is across countries in Africa. So very important also to know, I know that Yusra, you're also very active in that community. So it's certainly not all about IBM, it's really about building this community cross countries.
Hi everyone, my name is Eugenie. I work with the GSMA, so it's the Global Association of Mobile Operators. And I work specifically for the foundation called Mobile for Development. And so we do a lot of research on the role of mobile and digital technology for development, for impact. And so I lead research on that. And recently, in the past 2 years, we've been doing increasingly more work on AI. And so we did last year some reports on AI in Kenya, Nigeria, South Africa, where we were mapping out the ecosystem and looking at some of the building blocks. So data skills, but obviously as well compute. And now we're starting some new research on edge computing specifically, so building on that, on these reports that we did last year. Apart from research, we're also supporting local innovators in Africa and in Asia mostly. And so we provide funding, but we also want to provide some technical assistance. And obviously a key part of that will also be to work on the compute side of things and providing or working with partners to provide computing resources. Yeah.
Hello everyone. So my name is Robert Selemani. I'm from Cassava Technologies under the Cassava AI team. So about Cassava, we are a Pan-African technology company that is building AI factories in Africa through our partnerships with the likes of NVIDIA, where we are bringing the H200 GPUs to Africa, and we'll be building data centers in Cape Town, Zimbabwe, Nairobi, Kenya, with our planned expansion in Morocco and Egypt. So at Cassava, I'm a cloud platforms engineer, where I provision cloud resources, managing those resources, ensuring that they are as efficient as possible. I deploy AI workloads and monitoring those resources, ensuring that they are efficiently utilized. Thank you.
Hi everyone, my name is Kofi Abo. I work with Mozilla Foundation, and I'm a program officer with Mozilla. This is my second time at Indaba. We've been supporting Indaba since, I think, for the past 2 to 3 years. We've been supporting the main Indaba conference as well as the Indaba X event, both in Ghana and DRC in some time past. And so we're really a big fan of the community. In terms of compute, and before that also we, and probably something that is more concerned about this particular audience is that Mozilla runs a program called Responsible Computing Challenge. And what we've done in the past is we've invested more than over $5 million in universities across Asia, North America, and Africa, trying to support the faculty develop curriculums that teach computer science students the social and political implications of AI. And so that's the part. When it comes to compute, we have been engaging too on a high level with intergovernmental groups like J7, trying to position compute as a public good or for the public interest. Most of you here who are doing a lot of work around AI, especially for students, you barely have access to compute, and even if you do, you really have a minimum amount. And so the number of data sets you use are really small because you don't have access to a lot of them. So how do we position compute in such a way that's not just for commercial use? How do you convince government that they should invest in it just like they're investing in water, they're investing in electricity? And that's one of the things that we've been trying to engage government at that level. But when it comes to the regional level also, we've been having conversations a lot through consultations with partners like IDRC, trying to understand what the challenges and opportunities are both at the demand side and the supply side of compute. Thanks.
Yeah, thank you very much, Kofi. So a bit about myself. I'm Kai, the moderator. I'm a researcher with the International Development Research Center. And increasingly, we are beginning to look at compute as an area of programming that also means as we build out this responsible AI ecosystem across the continent with 13 and also growing labs and 9 innovation hubs, as well as 6 policy hubs. We are hoping to also support and build out that ecosystem with compute as a fundamental input. So what I'll do, we had a chance to kind of have some targeted questions to prepare for the panelists. And then we will, after that, we are going to have one more round of conversation around how do we move the conversation to make sure that we have more inclusive and responsible and even safer compute as well. Then we'll bring it back to the audience. Everyone here, please do engage, and then we might possibly have to kind of go into a bit of the lunch break as well. Please do feel free to remain for that before we close, okay? So I would like to ask the first question to Cassava, because you're on the ground, you're very active. There's a lot of excitement, like you mentioned about bringing H200 GPUs to the continent. Can you say a bit more about what are some things that you're looking and targeting as you're expanding into the African market, and then you're very well established, right? And what does the latest cutting edge high performance compute look like?
Okay, thank you so much, Kai, for that question. So I think you have been seeing through the media the wave of news about Cassava. partnering with the likes of NVIDIA to acquire the H200 GPUs. So those H200 GPUs are coming to equip our Cassava AI factory with targeted locations being South Africa, that is Cape Town and Johannesburg, then in Zimbabwe, in Kenya, then later on in Morocco and Egypt. So what we are trying to achieve as a Cassava is we are trying to make sure that Africa as a continent, we have sovereign computing resources, computing power, trying to, because like for those who attended the earlier session where Dr. Albert mentioned a bit, where the data is processed is really important, right, in terms of where, in which location is being run. On two aspects, in terms of policies, we are seeing our African governments advancing on.
There is a lot of technical teaching that happens and learning that happens in your courses and in your programs. And you get to learn about the social implications, whether it's how does your product you're developing affect somebody of low income or somebody who is of a different, whether it's a disability or any kind. You get to learn those implications later on after your program. And so what we thought of it is that for us to be able to embed some of these ethical principles and codes into machine learning and into the technical teaching, you have to redefine the curriculum of computer science programming in general. And so we work directly with faculties. And so, for instance, we provide, on our side, we provide the funding, and then the faculty will come together with other, not just the computer science faculty, but with other faculties, including humanities, to think through what are the possible implications that could be avoided now before the actual programming begins. And so students get the opportunity to sort of simulate ideas through the curriculum development. And so we make this also available and accessible to other institutions as well. So we have a playbook that also helps other institutions to be able to learn on how to design such ethical curriculum across their institutions. When it comes to computing, I think what we are trying to also avoid is exclusivity. In the sense that if you look at the internet revolution that happened across Africa, even though there is a lot of internet connectivity on the continent now, if you look at the research, a lot of the connectivity lies within urban communities and high-income communities. What about those who are in the rural communities? How do they access internet? It's always a problem. Mobile data is still an expensive commodity on the continent, and actually more expensive also for rural communities than any. Not just by the prices, but by also accessing power, electricity. So how do you think through all this to avoid the repetition of that happening with access to compute? So we are helping in that way to be able to see how do you provide compute to last mile. It's also another question we have to think about from an inclusion point of view.
Thank you much. I think that really well segues to Eugenie with telecom firms, but also your work on thinking around edge computing, right, which are more on device operations. Yeah, please.
Yeah, no, definitely. So I think for GSMA and for telcos in general, there's been a lot of interest, I think, in AI, and they're looking at leveraging as well edge computing as a way to reduce costs and improve operations. So there is a lot of interest for internal use cases, I would say. But as a foundation with Mobile for Development, we really want to look at more of the external-facing, user-facing use cases and solutions. And if we look at Africa, you know, it's mostly mobile first, what we call mobile first markets. And so there is really an opportunity to bring AI capabilities on the edge, on mobile devices. And we are seeing actually, maybe not a lot, but some innovators trying to do that, including on lower-end smartphones and smartphones that can work in low connectivity environments. So I think, as you're saying, there is a lot of work to be done in terms of reducing the cost of mobile internet use, even mobile ownership, and we're working on that. But I think in the meantime, if you think about digital inclusion as well, trying to find a way to bridge that gap and reach communities in at the last mile and using more of what we call legacy tech. There is a lot of opportunity there. We do have a lot of data as well on mobile ownership, mobile penetration, smartphone penetration. What we're seeing is that in the next couple of years, smartphone penetration specifically will really increase. So I think right now it stands at just above 50% of total connections. By 2030, this is expected to reach 80%. So there will be even more opportunities to use smartphones for AI and for compute. And this is something that we're looking at in this new research that we are doing, which is in early stages, but we really want to try and identify some of these use cases, edge AI use cases across different sectors, but then also kind of quantify the potential impact of increased smartphone and mobile penetration on the continent. I think as GSMA, we're also obviously interested in looking specifically at mobile phones, mobile devices, smartphones, but if you think about edge computing and edge AI, you also have other edge devices. This morning we talked a bit about tiny ML. You have a lot of tiny ML devices that can run on standards, kind of household batteries that can run for weeks. And we've seen some innovators as well, or researchers trying to leverage that for highly specialized use cases. So yeah, we're seeing quite a bit of opportunity there.
Thank you very much, Eugenie. Excellent. So next we have Petra, Quantum. So what is the build out of Quantum so far on the continent? And tell us why this is the big next thing. Yeah.
Yes, Quantum. When we talk about Quantum, you probably think about those very large machines that are very expensive. And it's true, we have those. We have those with clients or countries who wants to buy it and who really want to have a system on site. Think about Cleveland Clinic. They have a quantum computer in their cafeteria because they want to do some really tough research on it, but also attract talent and do activities around it. Japan has, Korea has quantum systems, Spain, the Basque country, has a quantum computer, and many more. But it doesn't have to be like that. You can also easily access it through the cloud. So we are on the cloud since 2016, and there are also accessing through the cloud has different modalities. So there is an open plan, which is free. So if you want to start building your skills, everybody here can access the system. It's 10 minutes per month. Maybe you say, oh, that's not much. But don't forget, for quantum computing, you first prepare on a classic computing, and then you do some shots to get the results. So for really starting to build your skills, just try it out. Then we have also, if you want more, you can also, of course, buy some access through the cloud, which is at a way, way lower cost, which is very accessible also for everybody. Also, what we also sometimes see is universities who really have a very interesting project. They say, okay, we want to have access just to do this project. Can we have some credits? And depending on the project, you just come to me and we can decide if we can also give you some credits. Credits means that you get some time on the quantum systems. As an example, some people in Egypt, they approached me. They have a hackathon early September, and they said, can we also for that hackathon have some credits so that we can also really try it out on the systems? So I provided some credits. So we also have a startup program. Startup programs, also, I think it's very interesting, certainly here in the countries in Africa. We can support you, and we can also provide you some access. So really, depending on what you want to do, so next to all the community work and skills development where we can support you, there is certainly also this access. We also have yearly a summer school which we had 8,000 people this summer. And I know that, Stephanie, you are very active in that. So also there, it's virtual, but you have access to all our SMEs or quantum experts. We have some office hours, we have some Slack channels, so really easy to get access and to help all of you to build your skills. So just reach out.
Yeah, thank you very much. So I hear there's quite a lot of building community and then also building the capabilities to actually access and actually learn about quantum as well. Thank you very much. So before we go into the next and the final round of questions on inclusive and responsible computes, and then we are going to hand it over to the audience if you have any questions, and I'm also mindful of the time. So thank you for being here as well. We have a survey that's developed by Kofi and Krupa as well on the for the Equal Compute Network, where we're trying to understand, kind of get some initial baseline on how compute is being used by you, by the Indaba community. So please do engage. The QR code is on here, and please do come and talk to us if you have questions about the Equal Compute program as well, which is soon to be launched. So let's bring it back to the panelists. So how are you thinking through what are the key ingredients when we are thinking about building a thriving, inclusive, and responsible, and we might even add safe compute for the continent? And what are some visions, or what are some key ingredients you see? And then maybe we can go through the same order. We can go with Robert first. Yeah.
Thank you so much, Carl, for the question. So for us at Cassava AI, we envision like inclusion as a situation where no one is left behind because of maybe because of their geographical placement, because of the resources that are available to them. So we are trying, by all means, to make sure that we are bringing the GPUs to the continent, right, as close as possible, so that whenever we are provisioning these resources, we make sure that we are mindful of the situation that is on the ground. So that comes to the issue of payment. We are going to make sure that our resources are payable in local currencies. That is, even with mobile money, your M-Pesa, based on where you are, we are trying to make sure that no, it's not limiting, like maybe you only have to pay with US dollar, like the international currencies, but make sure that you are able to pay it in the currency that is most accessible to you. And we are trying to make sure that they are as cheap as possible. Our services, our compute resources are gonna be slightly lower than the global hyperscalers with like a good percentage. So you are guaranteed that you're gonna get access to cheaper compute resources, which is, I mean, affordable compared to the global current offerings. We are trying to make sure that we also, because we also do provide, build AI solutions for like both for our internal infusion and external diffusion. So we are trying to make sure that also those resources or solutions are accessible to anyone. Like at the moment, we are building solutions that you are able to access, like your GPTs through like USSD codes. So that helps to ensure that those who do not have access to smartphones can actually get to interact with these technologies through USSD codes. So in summary, we are bringing the resources closer, home to the continent, then make sure that they're available in local currencies, make sure that they're as affordable as possible, and like we don't have rigid offerings, because for us, we see it more of partnerships than like client-provider kind of thing. We see them as partnerships. We see you as partners. We are trying to make sure that we meet you at your very own need as possible, and we are making sure that our resources are not only available to enterprises, but to researchers as well, to startups. We are seeing a booming of startups like focusing on preserving the African languages. The likes of, I think we have Equalize here on the deep learning in Daba. I've interacted with guys from Dawa Health. So we have Lelapa as well. So we are seeing enterprises coming up, both startups and the non-profit enterprises as well, and non-profit organizations. I know we have AI Eswatini trying to preserve the Swazi language, which you barely find in any of these ongoing like large language models or these solutions. So we are trying to make sure that we are as inclusive as possible. Whoever needs the resources should get the resources at an affordable price, and as accessible as possible. Okay. Yeah, so that's how we see inclusivity in our like, according to us, everyone who needs to access the resources should access the resources with easy and at an affordable price.
We would love to negotiate for sure. Yeah,
definitely.
So we are going to go to Kofi before Eugenie and Petra. Yeah.
Yeah, just to add to what Robert was saying. So also just to explain a little bit of what Kai meant by a network. So I know a lot of computer science. I'm not a technical person, so just to say the network does not involve any computing stuff. It's just a network of how do you bring together different groups to be able to ensure that folks can have access. And what we mean by different group is the private sector, the public sector, and academia, philanthropy. How do you bring all these groups together to ensure that everyone plays a role and also benefits from compute? So just to put the context. One of the key things, and back to the ingredient question you were asking, is all these different groups within that particular network have different interests. So Cassava will have a different interest because it's a commercial entity, and it should also have that particular profitable interest because that's the only way it will thrive. And so you have that legitimate interest, which is important. How do you complement the work of Cassava, who is very dedicated to ensuring that the continent has access to compute without losing? It's a question of which they will be interested is where is the demand, right? And so there is another part of that group that is supposed to look at that question and say, how do we provide an aggregated demand for compute to be able to go to Cassava and say, Cassava, we have this pool of market, and could you give us, a huge discount? This is me negotiating. But could you give us a huge discount based on this? And based on this pool, listen, we also have another group of amazing people, like the Indaba community or academic researchers who can experiment on your GPUs to show you the use cases that you're looking for. It might not be at a scale, but it can actually give you a fair idea of what the potential use cases, and the use cases might even turn out to be more commercially viable, right? And so that is the work of philanthropists and Mozilla Foundation and IDRC trying to work with Cassava, AWS, and all the hyperscalers, trying to understand and sort of pitch to them that in as much as you're looking at the profit angle of it, also look at how do you provide other resources to them. In addition, the framing here is that you have to harmonize all those interests together. And you do that by all the explanation that I gave. And so it's crucial when it comes to inclusivity because you shouldn't only look at where the profit margins are coming from, but you should also look at how do you serve the other communities that have long-term benefit. Because if this amazing group we have here have access to enough compute, this is where the commercial products are going to come from in the long term. But I hope those commercial products has a public interest focus at some point. Thanks.
Yeah, thank you very much, Kofi. And I think in the bundle of actors, we also have Gates Foundation, UK's FCDO, and then we're also engaging in conversations with the German GIZ as well. So it is an expanding network, for sure. Eugenie and then Petra, please.
Yeah, thank you. I think first, when we think about inclusivity, it's about different things, but the most important being affordability and accessibility and relevance, making sure that it's aligned with the local context, constraints and needs. And I think in many cases that means not copy-pasting things from different countries and maybe adopting more of a hybrid approach, looking again at the local context. So maybe that means leveraging cloud computing with distributed compute, edge computing. But I think beyond that, it's also about looking at the underlying barriers of inequality in terms of access to compute, and that ranges from connectivity to skills to policy. So it's also about the wider environment. And I think for us, GSMA again, some things that we're looking at are around affordability. So if we look at and connectivity, and so if we look at connection across sub-Saharan Africa, is actually pretty good. I think the issue that we're seeing is more about usage. So a lot of people, live in an area that is covered by mobile broadband, but they're not necessarily using mobile internet use because of, again, affordability, skills, and so these are some of the barriers that we're also trying to work on that will be really essential to leverage edge computing and more broadly AI solutions that are delivered, on mobile channels.
Thank you. And Petra, and then so after Petra, we're going to take 2 rounds of questions. So do prepare your questions as well, okay, in the audience. Yeah, Petra.
Yes, so I think your question had several components, but first of all, starting with the inclusivity and the accessibility, I think I already explained it that we can that we have free access and credits, but also we have a Quantum Innovation Center in South Africa. It's at the HPC Center, CHPC. So HPC, that's a supercomputer center, and they provide access to universities. So I think it demonstrates that it is accessible and it can be inclusive. So I hope that it will be spread beyond the borders of South Africa. So let's see how that moves. But I think you also mentioned responsibility, and that's really, I really like that question because it's important that we think about responsibility, not only for AI, but also for quantum. And there are different angles, of course. Responsibility, it's being conscious of not having that bias. I think that's important, and not building that in. So that's one thing that's important. But also, look at the use cases you're working on. Are they or these use cases that could also profit, have social impact, good social impact, so also an important one. And also be transparent. I sometimes hear people talking about quantum, and then they already promise return on investment within the year and so on. So be honest about technology if you talk about it. I think that's also very important. So that's I wanted to mention as well.
Thank you very much. Yeah. So I would like to have the chance for the audience to ask questions, please. I see there are 2 hands there. So let's take 2 questions together, and then we'll bring it back to the panel, and then we'll go back to the audience, okay? And then we can maybe do that twice, if not 3 times, if not more. Yeah, please, go ahead.
Sure. Thank you so much. It's been an amazing panel. I recently became aware of a company called Vast AI that provide compute on the continent at a very low cost. I looked at some of the quotes for, I think an A100, it was like $1 per GPU hour. And for like an H100, it was about like $1.50. This is some of the lowest costs I've seen anywhere. What do you think is the role of such initiative for this type of a conversation?
And then can we take the gentleman in front? Thanks, Howard.
Hi, mine is more of a curious question directed to Petra. Why is there continued research and investment in silicon chips despite the significant breakthroughs in quantum computing? And just to put it into more context, Google, like your company, has published research saying that some calculations that would take billions of years can be done in just minutes, right? And I would imagine that we as AI researchers would run some iterations in just a snap of a finger. Why isn't that the case? We are seeing NVIDIA publishing, I don't know whether the recent one was GB300, GB200. Yeah, that's my question.
Okay, so I'll bring it back to the panel. I'll let Petra answer the most recent one, and then we can open up to the affordability question as well. Yeah.
Not sure if I totally understood your question, but so we are currently we have a quantum chip which is 156 qubits. We do publish about it. We publish many papers, IBM only, but also together with our partners. I know that Google has the Willow. Google has, in fact, they are using the same technology as IBM, which is a superconducting technology. Indeed, this is what we expect. So we have, and during my previous talk in the other room, I, for instance, gave the example of the security, which is what if quantum computers can break the security algorithms? And that's really a very important and dangerous one. But that would take now, we estimate it at millions of years. With Shor's algorithm, quantum algorithm, it could take a few hours. So that's indeed where it becomes very dangerous. And yes, we are working on it, and we do publish a lot of papers on it. Thank you for the question.
Thank you. And yeah, I think there was a mention 3,000 papers from IBM research, right?
Yes, yeah. yes. Many papers are being published, and it's going really exponentially, which is good because it also means that people are interested in using quantum. And this is now, I only have the numbers for IBM, but it's good. People need to work on it because it's the future. And I also want to say again, it's the combination of quantum, AI, and classic computing that is powerful. And the integration of those three is very powerful. So it's not about quantum replacing classic computing. It's a combination. Thank you.
Thank you. So I will, on the question on affordability and that particular pricing, thoughts, and then answer if you feel gravitated to the question too, right? So Kofi, you seem to have the mic, or yeah.
I was going to give it to Kasava.
Robert, if you want to go after, yeah.
I think you can go after. Okay. No, but that's a good question because I think We also need the presence of local service providers to show that the cost of compute could be reduced. The reason I'm saying that is because it pushes the hyperscalers like the Google Cloud and AWS to reconsider what they are pricing for compute on the continent. I think there are also some advantages to that, which is affordability, but not directly cost-related affordability, in the sense that having access to AWS platforms and not picking on AWS, just hyperscalers in general, is there are quota restrictions, right? And so if you have a local provider, you are likely not to have quota restrictions, depending on if they are also providing the same service. But I think that lower cost in accessing locally would push the hyperscalers to reconsider. I think there is another startup in Nigeria that is also doing on-premise. I've forgotten the name, with a couple of others, and also integrating local payment systems. When that happened, it actually triggered AWS, Google Cloud, and other providers to start rethinking of adding local payment to their platform, because that was not existent. And I think even up to now, not all of them still have it, but at least it pushed them. So I think that is important to sort of push the big players to start thinking of alternatives.
Robert, and then afterwards we'll bring it back to the audience. And thanks again for being here. I'm mindful of the time, so let's continue. Yeah, please.
Okay, so I'm not gonna, repeat what has already been said by Kofi, but from the presentation that was presented in the other room by Dr. Albert, I found out that it's about only about 5% of the people who need compute resources in Africa actually has access to the compute resources. We are talking about your GPUs and stuff. Why is it so? There's a reason why is it so. So having players like ourselves, Cassava AI, we are trying to bridge that gap. We are trying to investigate why do we have that low access. Is it that because of the price is very high? Is it because of maybe the payment methods are not favorable to our current situation in the African continent, where we are having other countries like Malawi are struggling with the issues of like foreign currency and the likes. So we are trying to bridge the existing gap that is there to make sure that the issue of inclusivity that we are talking about is factored in. So for us, it's a matter of breaking the existing barriers that are there. And we have been seeing the ongoing tech wars within these big countries and stuff. Me personally, I would anticipate that we are going to have policies that are going to cut the access that we have to resources, because they are trying to survive that competition. So they are trying to reserve those resources for their own use. So what will happen to us as Africa if that happens? That's my anticipation in terms of changes in policies. So it means we need to have our own sovereignty on the African continent to ensure that we survive, we still have access whenever those things happen. So in summary, we have a role to play to make sure that there's inclusivity of those resources. So those low prices, like for us, like I said, we are offering discounted, we have a discounted offering that is definitely way lower than the hyperscalers. So it's there to make sure that everyone has access. Whoever needs it has access, and we are trying to break that barrier, making sure that whoever needs them, whenever they need them, they have the resources. Thank you.
Yeah, thank you very much. So what I'll do, let's maybe take one more round of questions, and then we'll bring it back. Please keep it brief, and then your responses also brief, as we do need to close. And then I will give each of the panelists a brief and sharp final word, okay? Please, Albert, I think, in the back. And do we have another question so we can couple it? Yeah, I think there's one as well, Emmy.
Yeah, thank you very much. Just to add, to say a point on what he said, it's possible to bring down the cost of a A100 or H200 GPU really low if you adjust the availability, right? I can offer it to you at $1, but I tell you I will only offer it from 12 to 4 p.m., right? Because that has a lot to do with energy measurements and whatnot and all that kind of thing, right? So that's very possible, but maybe we need to ask ourselves the availability question. My question is to Cassava. What's Cassava doing to ensure the talent that is required to run and build all this infrastructure they're bringing to the continent, one, is available and it's continuously going to be available, right? I think Amazon had to do a lot of talent building before they could even bring people on board the cloud. And the final question is to the moderator. It seems there's a lot of interest from funding agencies on this equal compute agenda in Africa. And I'm wondering what's the influence of that gonna be on the continent, right? I'm not seeing people from our governments on stage. I'm wondering what's that gonna look like for the continent? And can we as practitioners have a way to input what we need?
Great. We have two questions, one from the back, Emmy, and then one in the front. Let's take all three. Please keep your question short.
Yes.
If possible.
Yeah. Yes, Kai. So mine is quite related to his last point, and it's the question that Kofi started with. And I would like to it's a curious question, what's your experience on your expectation for governments to invest in this area? Is it something that they're going to do? Looking at the panel, it's made up of purely private sector, except maybe for yourself. Is it a realistic expectation, or should we just support them to do the skilling and the policy environment, etc.?
And one more in front, please. And thank you for that question.
Okay, thank you for the panel. My question is about energy. Like, we talk about computing, but it seems like the limits depend on energy. So how do you deal with that? Mainly the local player, like Cassava, and in some areas where energy is an issue, how do you have a plan for that? That's the question. Thank you.
Yeah. So I will bring it back to the panel, but I would like to target the fantastic question on funders and the various role that, let's say, IDRC can play within this compute ecosystem and market that's being built out. And of course, our AI for Development program, it's in partnership with UK's FCDO, and then our aim is to build this responsible, locally responsive, and inclusive responsible AI ecosystem on the continent. And what that also means, one of the fundamentals is looking at computes, but at the same time, has a research granting agency has our main mandate. We want to support local researchers first with our 12 to 13 labs, including here one on campus, to understand how they use compute, right? What type of compute do they need? And then we can begin to aggregate this type of information with our researchers and innovators in our network of AI4D, including Gates, and also the German GIZ ecosystems as well. And then once we can begin to aggregate that information, we can begin to have an interesting conversation, right, with governments on the ground. But at the same time, these are needs that are identified by our labs as well, right? So it's not us coming in, we're just providing that aggregation research and try to program around this. So with this, I would like to bring it back to the panelists. Do you have questions that you gravitate to? The energy one, what are the expectations going forward? Yeah, please.
Okay, so two questions were directed to me, the one on energy and the one on talent. Maybe let me start with the one on energy. Sorry. So our data centers will be equipped with a hybrid power supply that will leverage on electricity and renewable green energy sources. And since electricity can be unreliable. Sometimes we will be operating with a minimum of 48 hours of fuel for our generators. So that is a minimum of 48 hours worth of fuel as backup. And redundancy, we have redundancy in place for our data centers. And we also have partnerships with fuel suppliers that ensures that we get a fuel supply within 4 hours of placing an order. So that's our plan in ensuring that our data centers will be running continuously without any interruption. Then the question about talent, we don't believe that we don't have talent in Africa. There is talent in Africa. The question should be on where is the talent and how do we identify the talent. So we have platforms like the Zindi platform. We have partnered with the Zindi platform in terms of sourcing talent through their platform. So yeah, for I myself, Cassava found me through the Zindi platform. So there's a lot of talent that is there. All we need is to reach out and see what partnerships can we have. And also in terms of, like we're talking about the access to resources, like only 5% of people who need these resources having them. So with these ongoing partnerships, we believe in meaningful partnerships. So with having these partnerships in play, it means with more talent in Africa being able to access these resources, we are going to be able to identify that talent through the platforms like Zindi. And we also don't believe in partnerships where we just get the GPUs, they come in place, then what's next? So we are actually, as part of our partnership with NVIDIA, we will also be having training and certification programs to ensure that we build and upskill the talent that we have on the African continent.
Any other panelists who are?
Yeah, there was a question on government involvement, especially around investment. So there are some pockets of government investment happening. It's not directly investment around purchasing GPUs or building HPC centers here, but it's more around, so for instance, just an example, during the Global AI Summit in Africa, Gates Foundation, together with the government of Rwanda, set up the AI scaling hub, if I'm not mistaken. And part of that is also the provisioning of compute. So it might not be like, that direct, but it's creating the environment and also favorable policies. I know that some countries like Kenya, when you're purchasing devices, compute devices that is for research purposes, there are some waivers on import duties. And I'm sure it's similar probably in other African countries as well. So those are a place to start having conversations with. And here I'm going to take off my hat as a Mozilla, but as an independent researcher to add this to it, that when it comes to African government and digital transformation activities, it's always about what are the electoral incentives at the end of the day, right? If the electoral incentives are high, if they can physically see jobs being created out of it, then they are more likely to put actual money and give you all the incentives. But with time, I know that with time, with the investment that is being made and the use cases that will come out of it, probably they'll be more convinced than ever to be able to sort of invest directly. Thanks.
Petra, please.
Okay, this is better. Yes, I think it's really good question. Same for quantum, by the way. We see that governments are really play a really important role in the funding. And that is also where we are going to governments to explain why it is necessary, why it's now needed to start building your skills, to have these programs at universities. But therefore you need also, of course, to show what is the economic growth potential, what is the job creation potential, and so on. So it's a really good question, and we shouldn't minimize the role of governments there.
Yeah, and for sure, for the layer on energy and sustainability is something that definitely undergirds the advancements of this type of build out, right? So with that, I would like to ask Krupa to come up as well, just as we're closing this. If you want to come up, come. So like she also has been this wonderful powerhouse to actually convene and also co-organize. Thank you very much for IBM research and the many individuals who were helping out with the quantum and also compute workshops. I would like to have the chance to give the panelists a final word before we officially close. And thanks once more for everyone for being here, especially as we go into our lunch time as well. So Krupa, do you want to say a few words before we give our panelists their final words, and we have little goodies too? Yeah.
Yeah. Thank you, Kai, and thank you to the panelists. I think it was really engaging and interesting. We're able to host these workshops because of the interest coming from our audience. We would love to continue and improving these workshops for you, both the quantum computing, so QML in Africa, as well as the compute workshop. So this panel has been a joint collaboration in doing so or it's all part of like coming together as an equal compute network eventually, right? So we would love some feedback from you guys. There's a survey up there. If you guys can just scan the QR code, you'll be directed to a Google form, and we would really, really appreciate any feedback you have, any constructive feedback for that matter. So thank you for coming. I'll let Kai take the honors of giving a token of appreciation to our panelists today.
Yeah, so before we do that, wait, let's actually give them the final word. Then we will give them a round of applause, but also to Krupa and also IBM Research as well. Thank you. Please.
All right, I know that we need to be crisp. So I would say start now. Quantum is not a dream, it is the future. If you're bored of AI, just look at quantum. Thank you.
Yeah, I'll try to be short as well. I think first it's looking at AI, we often think about kind of the latest, cutting edge technology, which obviously is really important, but then thinking about inclusion, digital inclusion, I think what is key is also to leverage, combine that with legacy tech and make sure that no one is left behind in the AI revolution.
Thank you so much for your time and the important questions that you asked. So for us at Cassava, we are simply saying we have a humble ask that we have done all we could to secure the resources and build the infrastructure. May you please use those resources that we have secured for you. We guarantee you that we are committed to make sure that they are as affordable as possible. So if some of you have, I know I may not have managed to interact with some of you. I've been circulating an interest form on the Slack social channel. Please check it out. I also circulate it after this panel. Those who need the computer resources, there's that interest form. You fill it in, then my team will be able to get back to you to discuss about your compute needs. Thank you.
I would say that while others are interested in investing in the hardware of compute, I would make a call and say others or other partners should also look at investing in communities like Endeavor to increase upskilling to be able to increase the usage of compute. Thanks.
Okay, so I would like to invite, please, and then I want everyone to give a big round of applause as we recognize our panelists for their wonderful contributions. And please, would you like to share? Yeah, thank you very much again for being here. And maybe we can take a group photo for those who are here. And then I also want to recognize Krupa's great work. She's been behind the scene for the panel, but she's been essential. And then thank you once more for the quantum workshop partners as well. Yeah.
We have a few posters from the abstract that was submitted, some great work by Regis. Billy, and it will be Shawel online. So we'll start off with the VPNs, and I think you guys will find it very interesting.
Okay, so hello, everyone. I'm not going to take too much time. I'm Regis Ngesan from the African Institute for Mathematical Sciences. And today I'm going to present one of my papers, v-PuNNs, the Vanderput neural networks for transparent ultrametric representation learning. So what we are trying to do here is to solve a problem. And what is that problem? Actually, with deep learning and machine learning and whatever learning paradigms we have, we're flattening the data. What does it mean? Actually, let's think about it as this bottle, like your data. And what we are doing in deep learning, actually, is like we are trying to take an image of this bottle and to flatten it like from a 3D image to a 2D image, and we are processing information on this 2D image. So we are losing too much information from this transformation. So what we are trying to do here with our v-PuNNs is that we want to compute information or to learn information directly in the native space of the data, so the ultrametric space, or what we call the p-adic space. So let's talk a bit about the geometrical aspect behind this work. So in fact, in a hierarchy, everything like a tree-like data, or a tree-like data set, or a graph if you want, you have something like we call the node. And the node in a tree can be represented in a p-adic analog as a p-adic number in the ring of Z sub P. So we have also what we call and what we know as a subtree. So a subtree can be seen like, as a p-adic ball in the p-adic world. And also we have what we call the LCA depth. The LCA depth is the lowest common ancestor. So it's the way for us to compute the triangle inequality to evaluate a distance than the way we are evaluating distance in Euclidean space. So the implication here is that we are treating hierarchy directly is an ultrametric space. So we don't need to approximate, like to change a 3D image or a 3D data to a 2D data before processing any kind of learning stuff. So let's say here we are going from geometry to a neural network. So all my work is based or is inspired on the work of a famous mathematician called Marius Vanderput. So in number theory, it's well known as the Vanderput basis, saying that we can approximate or we can express function as the p-adic balls through this basis, through this theorem. So this is what Vanderput's basis is saying actually. And for acknowledging the work of this mathematician, I decided to name this new class of neural networks after him. So some key properties that I use and I designed here are also some theorem that I introduced for this paper, is that the transparent ultrametric representation learning, saying that here each neuron is going to be affected only if the element we are looking for is in the ball of this p-adic. So if and only if this element is inside the subtree we are looking for. And also that we are going to see that we can also process an OK balls along the route to the leaf. What does it mean? So in terms of optimization, it's extremely fast with our work to process the learning. So for the formula about the v-PuNN model, if you want later we can talk about it. It's going to be long for a 5-minute presentation. So here is the theoretical guarantee. As I said, it's not just about computation. Our work is based on mathematics to computer science. So what we did is that we introduced a new theorem called the finite hierarchical approximation theorem. Because everything we are doing in deep learning is based on universal approximation theorem. And this one is working because we are in an Euclidean space. But when it comes to work in what we call the p-adic space, this is a discrete space. There is no continuity. So every function, so any loss function here is piecewise continuous. So for that one, UAT, so universal approximation theorem, is not working. This is why here we introduce a new theorem proving that any function as a k-level tree, any hierarchical function as a k-level tree can be represented or approximated by a v-PuNN. And the other stuff we introduce, the other theorem, is that parameter subtree duality. So for each weight, here the weights, we call them CB. So they are kind of p-adic ball. For each weight, we are proving that a weight has an influence only and only if the input is the subtree B. So if the input is the node we are looking for is in the subtree B or the p-adic ball, this is when the weight is going to have an impact. Either that, no. So this is what we call the third principle, so the transparent ultrametric representation learning principle. So it allows us to have a fully interpretable model, what we call a white box model, instead of the black box model we have in deep learning. So let's talk about a bit the practical implementation. So the practical implementation that we did is v-PuNNs is like the class, a novel class of this neural networks, and HiPaN is like the hierarchical p-adic neural network is one of the neural networks under this new class. So here is the design, or I'm gonna say the diagram of this HiPaN. So we are just trying to predict from the digit root to the digit leaf, everything that's gonna happen. And for doing that, we are using the ultrametricity of the space. That means we are computing the distance through p-adic properties. This allows us to really, really reduce, or I'm gonna say in some cases, to even cancel, not really, really cancel at zero, but we really have very, very small loss in terms of computation of the distances. So this is what we are doing here, in fact, with the HiPaN. So let's talk about the characteristic of a ball neuron. It's a lot of mathematics. I'm not gonna allow you. If you want, we can explain later. I can explain later during the poster presentation. But what we have to understand also here is optimization that we know, like stochastic gradient descent or anything based on gradient descent, is not working in that space because, as I said, this space is discrete and not continuous. So we introduce also optimization family called VAPO, and we introduce two variants of this optimizer for being able to train such a model. Here we have some results. We train on very big data sets in NLP field, also for proteins classification, and also for some taxonomy. And we are able actually to have excellent results only on CPU. So when you, sometimes you are working on this same data set, you have to use GPU for having good results. Here, we are using only CPU for having results in minutes. So the time is just in minutes and not hour for such big data sets. So this diagram, this heat map, is showing that everything is perfectly ultrametric. So everything is perfectly classified compared to when you are using Euclidean distance. Everything is well separated. And this is one of the strengths behind using the p-adic properties. So here we have some baseline comparison when we were training. Compared to MLP, we were able to overperform MLP and XGBoost, even quantitatively and also qualitatively in terms of interpretation. These models are opaque. This is why sometimes people are talking about black box models. But here we have white box models, as I said previously, with exact subtree semantics. So we have fewer parameters too, and we are working only on CPU, no GPU involved here. So here, maybe I'm going to explain more of that part, but what you have to understand that is that behind this kind of representation, we can do the same in quantum computing, actually, for representing quantum states. Yes, so due to the time, maybe we're gonna talk more about it later. And as a conclusion, I'm gonna say that this is the key achievement we have: a geometric fidelity, a good interpretability, theoretical guarantees with the pure maths behind, and the well-demonstrated theorems, on computational efficiency, and some other application, because v-PuNN is going to be also a new scientific instrument for physics, for AI, or whatever you want. So we are investigating. Thank you, and I'm open for your questions.
Thank you. We're going to introduce our next abstract that was submitted. Thank you, Billy. Please come up.
Okay. Thank you so much. I'll try by all means to be as fast as possible. So my name is Billy Peter Mnyenyembe, and I'm working as a lecturer, but my background is in software development and space science physics. So what I have here is actually a work in progress research that we've been doing for close to 2 years now. It's basically about a robot assistant MD, where we intend to use quantum machine learning for real-time prescription validation, particularly to combat antimicrobial resistance. So maybe before I talk much about the same robotic assistant, I'll first talk about the problem that we're trying to solve. So we're trying to solve a problem which is basically antimicrobial resistance. I would define it as the resistance of certain germs or maybe fungi or viruses to certain antibiotics. So you'll find that sometimes maybe you take certain antibiotics and they would work, and then you reach a time where when you take, nothing would happen. That is basically what it is all about. Now, why talking about this one? It's ideal because according to the report by World Health Organization, about 1.27 million people, they die every year with infections directly directed to antimicrobial resistance. And about 4.95 million, they also die with infections that are related to antimicrobial resistance. And as if that is not enough, there's a projection that if there's nothing that will be done until the year 2050, about 20 million people will be dying because of the same. Now, we sat down and actually came up with the major causes of antimicrobial resistance. And amongst them, I want to talk about one because that's our major concern. It's a long prescription of drugs, prescription of drugs. So you come to realize that 25% of the prescriptions that we get from OPD are actually wrong prescription. That's according to research. So that's a major concern. So it means if we can handle this problem, likely we know that we can reduce when it comes to death caused by antimicrobial resistance. So therefore, that's how we introduce our robot assistant, which is basically a robot that will be working hand in hand with a doctor. So it's like a robotic companion. When the doctor is doing the prescription, the robot also is listening and doing its own prescriptions. And then at the end of the day, when the doctor is done, it can validate and best advise if there's anything that needs to be changed or if the doctor can keep up with the same prescription. And that's optional for the doctor. But if the doctor continue with the same, then there's information that will be stored somewhere which can help when it comes to model training. So we intend to use quantum machine learning because we know that it has a number of amazing models. For instance, we can talk about variational quantum classifiers that can really help when it comes to detecting even smallest differences between patient groups. So I'll go direct to the last part, which we anticipate at the end of the day when it comes to this. So we anticipate to reduce prescription errors because one, the doctor will know that there's something that is trying to validate the prescription and they'll be careful when it comes to prescribing medication. And also, if there's any error that has been made by the medical personnel, then the robot basically will be there to guide. And by so doing, we are so certain that the number that I initially mentioned, about 1.27 million, will definitely reduce, because the biggest challenge for antimicrobial has been reduced. So thank you so much. I think if there is more, I have a poster there. I'm more than happy to actually attend to those questions.
Okay. Shawal, thank you so much for joining us. So he's based in South Africa at Wits University, and he is supervised by Dr. Isaac Napi, who is one of the leaders in quantum photonics research in South Africa. So we are very excited to have him present some of the work that he's been doing. And over to you, Shawal. Thank you for joining. I know it's been a long day for you, but we really appreciate the talk that you'll be giving.
Awesome. Thank you so much, Steph. Hello, everyone. Thank you so much for having me. I'm quite excited to be presenting this work to you today. My name is Shawal Kassim. I am a PhD student at the School of Applied Mathematics at Wits University in Johannesburg. And today we'll be talking about classical and quantum convolutional neural networks that focus on image reconstruction in the low sample ghost imaging. Now, before we start off, I would like to share with you one of my favorite quotes from my favorite scientist, John von Neumann. The sciences do not try to explain, they hardly even try to interpret. They mainly make models. So this has been what we try to do, is we're not trying to describe what happens here, but we try to build a model that can mimic the physics that we're trying to do. Now, first of all, what are classical convolutional neural networks? In plain, simple terms, these are neural networks that deal with images, and the networks will try and draw out insights from these images, be it face recognition or image classification or object detection. Some of the application areas, as I've mentioned before, would be image classification, object detection, facial recognition, and the area of focus that we'll be looking at is the ghost image reconstruction. Now, what is ghost imaging? Ghost imaging is our very first quantum image reconstruction that was designed, and we are able to reconstruct images without having direct photons hitting the object that we're trying to create. Now, how does this happen? So we have lasers pumped into a crystal. This NLC is called a nonlinear crystal. And what happens is it splits the light up into 50-50, and the photons on the other side are entangled. And some of the photons that hit the object on this one arm, we measure its pair photons on the other arm, and we collect data through a coincidence counter. And all this data gets sent to a computer, where we will go and reconstruct the image. And essentially what we are doing is reconstructing spatial information, and the photons never interacted with the object we are reconstructing. Now, the setup, we have two arms. We've got the idler arm and the signal arm, and we use a very famous projective basis called the Walsh-Hadamard masks. These help us decompose our image into masks that we will later reconstruct. The image that we are reconstructing is an n by n image. It has both a real and a complex part to it. So in order to reconstruct this image in this experiment, we need 2n² measurements. Now that's a bit much for us to do. So we want to come up with a protocol that if you measure at least half the image, we can reconstruct this image. Now, how do we decompose our image? Well, if you look on the right here, we can see we have our original image I. This is the real and complex part, and we can decompose it into a linear combination of masks. The coefficients you find in the front here are known as the Hadamard coefficients. And these coefficients are proportional to the probability of photons occurring in a certain mask. And there are n² coefficients here. What we are trying to do is we're trying to re-represent our image in the Hadamard basis. And why do we do this? Well, it's computationally efficient, as the elements in the matrix are only +1 and -1. Low frequency components contain important information, while high frequency components contain the noise and sharp features. And what is nice about the Hadamard transform is it's prone to very noisy channels. So as you can see on the right, we've transformed our spatial image to the frequency domain, and then I provided a surface plot on the bottom here just to see the contribution from the basis vectors. How do we construct our data? Well, on the left here, we have the image we're trying to measure, and we leave out this plus sign. These are the pixels that we won't measure, and then we'll transform our image to the Hadamard image, where you see the purple, we don't know what pixels there are, and we hope to get out a fully reconstructed set of Hadamard coefficients, such that when you do the inverse Hadamard, we get back our real image. Now, these are 32 by 32, and the purple area you see here is almost 44% of the image. So we have 44% missing information. So we are just trying to get the CNN to reconstruct this low sampled set of images. Now, can we use convolutional neural networks to reconstruct low sample images? Yes. And how do we do this? Well, first of all, we try to reconstruct just the real part of the ghost image, and we'll train it on some data. But how do these CNNs extract features onto low dimensional spaces? There are two important things I want to talk about. It's convolution and pooling. Convolution will extract features from our image, while pooling will reduce the dimensions of our image by a half. So if you have an n by n, we can go down to n over 2 by n over 2. This is just an example of how the convolutional layer works. So we have some kernel that slides across the image with a stride. This GIF that I presented here has a stride of 1, and we just multiply the weight coefficients with the input image and get out a new matrix. These extract our features. The pooling layer reduces the spatial dimensions of the feature map. As you can see, we go from a 4 by 4 image to a 2 by 2 image. Now, these convolutional neural networks assist neural networks to handle high data. And how do we do that? We can take any 2 by 2 image or signal, and we can encode it down to a low dimensional high feature tensor. This means we can represent high dimensional n by n images on a very low feature tensor that we can feed into a fully connected network. So data is encoded to a size that can be fit onto a fully connected layer. Now, could we expect any performance benefits if we were to use quantum machine learning? Yes. If we use quantum machine learning, quantum superposition and entanglement, we're able to learn more intricate and nonlinear patterns. And can we build a quantum analog of the convolutional neural network? Yes. So what do these quantum convolutional neural networks look like? Well, on the left here, we've got a picture of a quantum circuit. What we do is the quantum convolution and pooling is done on a quantum computer. And once the data has been compressed, we feed this back into a classical computer that contains our fully connected layer. Now, there are some important characteristics of these circuits. They make use of variational parameterized circuits. They do the same thing as convolution and pooling, and these circuits can be implemented with reduced circuit complexity. So we're hoping to reduce the computational operations here. Traditional QCNNs are hybrid models. So this is a paper that came from a medical science paper, and they try to reconstruct MRI brain scans using both a quantum computer and a classical computer. The quantum side handles the encoding and feature side, feature extraction, while the classical side will update the parameters and handle the optimization. And it handles our fully connected network. Now, to use CNN in ghost imaging, our aim is to reconstruct missing Hadamard coefficients. We'll use the convolutional and pooling layers to extract features and put them onto a smaller dimensional space. And we have seen that CNN models have higher test accuracy and are faster at training than normal fully connected neural networks. Here is a visualization of our model, of a classical model. What we put in is the low sampled Hadamard coefficient, and what we hope to get out on the right-hand side is the fully reconstructed set. And then in the fully reconstructed set, we will do the inverse Hadamard transform to get the spatial representation. Now, a benefit of the Hadamard transform is that these coefficients retain a lot of the features, so this makes it very prone to the noise channels that we're talking about and error. Here is an overview of our classical CNN. We use PyTorch to build this model, and the specific CNN that we try to build is called a UNet architecture. So we'll see the first half of this network is called the encoding layer. The bottom half is called the bottleneck. This is the most compact that the data is. And then we'll upsample this data back to the original image, which is 32 by 32. So just to give some reference point, this bottleneck ends up becoming a 4 by 1 vector with about 4 times f, where f is the filters that we're using. Most importantly about this network is we use skip connections. So we can take data from the convoluted layer before a bottleneck and transfer it to after the bottleneck. This helps us retain some of the spatial features. Here is a first attempt. I tried to run this at the cluster at Wits University, and it took a few days to run this first attempt. I used the Adam optimizer with a learning rate of 10 to the negative 3, and all this data has been trained with only around, at most, 10 epochs, and the training time is less than 5 minutes for each model. And I did hyperparameter tuning on each parameter you see here. So this is what took days for it to complete. What I did then is I tried to decrease the filters and change the batch size. And in doing so, we were able to get a better reconstruction of our images. Here we have run the model for 500 epochs, and at most it took about 70 minutes. And we see the best performing model here. It uses 32 filters with a mini batch of 250. The entire training data set is 60,000 images, and we are using the MNIST data set. Now let's go on to the quantum computing models. We used 2 models. The first model we got to run, but the second model we have not finished yet. So I'll produce the first model. This one is called the quantum autoencoder. Its main purpose is to compress quantum data onto a lower dimensional space. And what is important about this network is we have no skip connections. This model is solely used to compress and then recompress data. We use Qiskit machine learning to build this model. And even though it's only involved in data compression, we have forced the model to reconstruct images. And we did this by giving it specialized data, which is noisy data and then the ground truth data. Each of the images that we're looking at is 32 pixels, and we take 5 qubits to encode this. They get compressed down to 3 qubits and then up compressed back to 5 qubits. And what we see here is it's able to fill in the missing pixels. So what you're looking at is the first ever iteration of using data compression to reconstruct quantum data. Here is an example of our run. We noticed that these quantum models they don't take too long to train, and they only require 1 epoch. This model took 40 seconds to run, and the goal that we tried to focus on here was strictly just data compression. How much of the data can we return back? And we got quite a good representation. We then retrained the model with the noisy data and missing pixels. This took about 343 seconds, again with 1 epoch, using the Cobila optimizer. And if you look on the right here, we can see pairs of images of the reconstruction. So if you see this first pair, this is what we put in, and then this is what we get out. The same for the 0 over here. We put in this 0 image with missing pixels, and it's able to reconstruct. So we got some really good results from this. Now I'll go on to presenting our second model. We tried to build a quantum analog of the UNet network that I had spoken about earlier. Here we introduced skip connections.
Sorry, Shawal. Just keep mind of time.
Okay, I'm almost done. Yes, thank you. In this model, we incorporate the skip connections. We had built the convolutional circuit layers, and we built it according to some paper. We did this with parameterized unitaries. We did the same for the pooling layer, and we did the same for the deconvolutional circuit. So this circuit takes in n qubits and scales up to 2n qubits. This is an overview of our entire model. It goes from 8 qubits down to 2 qubits, and it upsamples back to 8 qubits. We are yet still to test this model, as there is no such UNet model available for quantum computing. So yes, we are yet to produce results on this, but we are happy to say that we managed to create a classical convolutional neural network that can upsample low sample data, not just on ghost imaging. Thank you very much.
I check 1, 2, and 2. Thank you, Shawal, for the fantastic presentation. Yeah, I think it's finally the end of the workshop. We thank you all for coming. It's been really fun.